Good morning. Good morning and welcome to this very first MedTech Day, TUE MedTech Day of Eindhoven University of Technology. I would like to welcome you all for coming. Thank you very much. I think we have a great program. I'm looking forward to a great day. I saw discussions already started, so I'm very happy about that. I would specifically, of course, like to thank the speakers of today. And I also would like to introduce the topic of today, which is the Golden Triangle. And the Golden Triangle for us stands for the collaboration between academia, industry, and the clinics. And we believe this is a very important concept because, of course, academia is important to develop new ideas, but we need also the collaboration with industry to make it happen. We need the collaboration with clinics to get the right questions, or to answer the right questions, to solve the right problems, and also to implement and validate. So we believe this concept is really the key to success. I would also like to introduce the program of today. So first we will start with the opening. We have a session on neurology. Then there's the coffee break. We have a session on in heartbeat, which is cardiology and perinatology topics. Then there is the oncology session. And finally, of this day, there is the wrap-up. After that, of course, there's the inaugural speech of myself. I would like to introduce also the person who will introduce, basically. But I don't have to introduce her, I think, because our first speaker is Carmen van Wilsteren. And I don't think I have to explain her role in healthcare, but I still will. We all know this great woman, great leader. I think very important here at Eindhoven University. She is the chair currently of the top sector, Life Sciences and Health. I have to read this, sorry. But she also has an extensive experience in industry with both big enterprises at Philips, but also small as a startup. At Eindhoven University, she is the chair of MedTech, which is our big collaboration program. Maybe she will explain about that. And as such, she has an important role in setting up public-private partnerships. So with this, I would like to invite Carmen to the stage.
Thank you very much for your very kind introduction.
Microphone is working. No. Maybe.
It's working now. Okay, I'm happy it's not in my bag, so I don't have to turn my back to you, so we just can fix it like this. Well, thank you, Maarten, very much for your kind introduction, and also very much welcome, of course, on behalf of me on this very first MedTech Day on the Eindhoven University of Technology. I was also asked to put this in a little bit broader perspective with my national role on, as Maarten already introduced. And the top sector, very brief about that, is being established by the government after the financial crisis to stimulate innovation in the Netherlands. And that's been turning on quite successful. There's been 10 top sectors, but a couple of years ago it is evaluated and it said, well, it's nice to have this innovation and also economic advantages, but it's also good these top sectors can also work on our societal challenges. So the Rutte 3, our last cabinet, has defined 4 societal challenges, which you can see here, and care and health and care is one of them. And we have a number of long-term missions, you could say moonshots, that are defined as a kind of goal for the Netherlands in 2040. And for health and care, it is that our ambition is that in 2040, people, now I have to walk back, I can see it here. We want to have all our Dutch people to live 5 years longer in good health. So not only live longer, but live longer in good health. And the most difficult part of the mission is that the inequalities in that ambition between high and low social classes have been reduced by 30%. So right now, who knows what's the average life expectation difference between high and low social class? Does somebody know? Probably you do know. How much? 7 years. 7 years. So reduce that by 30%. And we also know that in COVID time it has not been reduced, it has been increased. And you see MedTech is playing a role in all these 4 sub-missions that has been defined. The first sub-mission is about prevention. The second one is about taking care at every place. The third one is about chronic diseases. And the last one is people with dementia. We know in 2040 dementia will not be solved. So it's very much about early detection and increased quality of life of people. And I will give a few examples next to what we will have today, because there are many technologies presented today. I will show a couple of other examples of medical technology in these 4 domains. The golden triangle is also part of what we call the quadruple helix. You can say it's a kind of square around it. So we talk the missions, we very much involve patients, but also citizens, in combination with industry, in combination with science, and in combination with government. So public-private partnerships, we still talk about that, but then we include also the citizens and the patients into that. So you could say it's a kind of square around the golden triangle, but don't worry, I will show also one of the golden triangle examples, Maarten. Well, I also mentioned prevention. It's good to be aware that the extended life expectation of people in the last 150 years is about 40 years. And you see here, about 100 years ago, you need Photoshop to put 5 generations into one picture. And now, well, it costs a little bit of effort, and it's not perhaps for everybody as convenient, but we can have 5 generations in one picture without Photoshop. But it's not about, that's not caused by medical technology or about medical knowledge so much. It's only 15% of this extended lifetime. The most important things has been things like hygiene, clean water, social laws, better work circumstances, and so on, education. So medical technology and medical knowledge has only been cost 15% of the extension of the life expectation. Well, this has been quite slow. Sometimes technology is moving faster. You see here 2 different Pope inaugurations. That's only a couple of years in between. I think it's been about 8 years, and you show completely different picture, completely different experience because of technology. But still, behavior doesn't change so fast. So that was about prevention. An example about availability of care. This is the development of a careable neo-kidney. So people that has kidney problems, they go to the hospital right now for dialysis. And the Kidney Foundation, with a large public-private partnership, has been working quite a number of years already about doing that anywhere. They started with a kind of belt, but then the patient said, well, that's a little bit stigmatic. I don't want to be shown as a belt. So they changed the concept into a mobile concept that you can use literally everywhere. And then, of course, we all know, and also Eindhoven is quite active in that, the next step will be regenerative medicine to stimulate the body to heal itself. Well, availability of care is also one of the big topics in MedTech, which is the second session of today. And MedTech is the Eindhoven MedTech Innovation Center. It's basically the continuation of very long-term bilateral and trilateral collaboration in a partnership of 5, exactly, as I've been told, industry, the university, and the clinics. And it's also scientifically shown that the success of this kind of collaboration is dependent of the excellence of the partners, but also of proximity. And we always talk about the bike distance of all these partners. And it's literally the case that our PhDs, but also the employees who work in this ecosystem, are in the morning at the TU, in the afternoon at the Catharina or whatever, and in the evening we have a pizza sessie at Philips. The mission of MedTech is to fast-track clinical innovation by value-based healthcare. So innovations that add value for the patient and speed it up. And it's really a big ecosystem. It's still growing, and it's about 100 PhD right now. And one of the biggest things is also that we are educating our talent. We all need it. The healthcare is changing quite a lot with all kind of technology, with more patient-centric. And the PhDs in our ecosystem are used to work from all kind of different angles, look into the problem from an industry point of view, from a patient point of view, and from a science point of view. So there's the triangle again, Maarten, so don't worry. One of the examples is remote monitoring. The health dot is one of the examples where you can people, after a surgery, let go home much more earlier, but in a safe way, monitor them at home. This is another example here from our university. We have quite a number of student teams, and one of the student teams is also working for people with chronic disease. They're trying to translate people that have difficulties with communication into tactic feeling. So it's very nice to see our students teams around. And it's a little bit pity. We all know our mobile student teams with Lightyear, but there are also very much medical student teams, and it's not so easy to bring it into the market. But you will see in the future much more from our student teams here at the TU as well. Well, people with chronic disease, we all know the topics around interventional, cardiovascular, oncology. I think that will come today much more broader also in the sessions. And AI, of course, is playing an increasingly big role into that. Last example I want to show is for people with dementia. That's also one of the groups here at the university. So I'm going from the Netherlands now to the university back before I will introduce the next session. People with dementia, this is one of the developments of also one of our professors. This is a home compass really developed from the thinking from the person. So, all kind of GPS solutions. That's all to help others to find somebody with early dementia back. This is for people for a person with dementia. There's only one arrow on this product, and that always pointed towards home. Very easy product, very easy concept, and it's really thinking from the person, the patient itself. Well, I think that's what I wanted to tell you as an introduction for this really nice day. I'm really looking forward. I already congratulate Maarten up front as the first person with your inauguration. That's the advantage you have here with your mic. And I would like to ask Noortje to take over for the first session. Noortje.
Thank you. Good morning, everybody. I also like to welcome you to this day, and I'm really happy that we can meet face to face because a lot of people I only remember from my screen. So I hope that we also have some time left that we can interact. Today we start off with a neurologist session, which is called Cooperation in No Linear. And for the Golden Triangle, we have Professor Cyril Bijnaert from Amsterdam, who will present our academia. Evelien Cadet from University of Ghent, who will represent clinics. And to close the triangle, we have invited Dr. Jurriaan Bakker, who's working in inertia.
Geluid staat niet aan.
Who is our clinical component of the industrial component of today. And the session of today will be moderated by Prof. and Bert Alderkamp from our university. But before we go to the session and to the speakers, I would like to start with a tradition of the Center for Care and You. We bi-monthly organize a Yeah, I see people already started filling it out. So the question is, how is it possible that some of you in the audience see this dress as a black and blue colored dress, but that there are others that see this dress in white and golden? Is the answer A, how you see the dress depends on the way the dress is displayed. For example, now it's on a beaver, but when it's on paper, it can be hidden. Answer B, some people see the background of the dress as brighter or darker, and therefore the brain interprets the colors differently. Answer C, interpretation of the wavelength
Ja,
of light
ik zie altijd goud.
That's why some people interpret the wavelength of blue as white in the shadow. Answer D, some people have a special form of color blindness, which is not regularly blue or red, but different, which they don't know. And I see that there is people are still voting. I give you a couple of seconds. It's answer B or C. People are in doubt. The correct answer is answer C. The interpretation of the wavelength of light depends on the context. So that's why some of you see it in blue and others see it as white. Second question. How much investment money and years of development are necessary to bring new neurostimulator systems and therapy to the market? There's somebody really quick. I think we have that we all are. The audience is in almost a sort of agreement.
Ja, 3 jaar.
I think you already are a quite experienced audience because indeed the right answer is D. It costs $100 million dollars or euros, and it takes more than 10 years to bring a neurostimulator to the market. Final question of this neurology session. For those who studied medicine, they have an advantage. Which Latin word is the vagus nerve named after? Is it A, sensitive, B, wandering, C, complicated, or D, benign? I thought that the question was quite complicated, so I'm curious if the speaker of today knows what the right answer is. But again, I think we have really nice experts in the audience today, because the answer was indeed wandering. With a small pub quiz, which will I give every session of today, I hope that you got excited about what's gonna happen in the session. And therefore, I would like to give the floor to Rob Mestrom and Bert Aldekamp to continue with the session. Er gaat iets mis. Hij wil niet wisselen. Alsjeblieft.
Yeah. Thank you for the nice pub quiz. I think this set the tone for the 3 talks. Well, welcome to the first session of 3, in which we investigate the cooperation between industry, the clinic, and academia. And this session is themed neurology. So there will be 3 talks: one from industry, one from academia, one from the clinic, on neurology and neuroscience. And I would like to invite the first speaker to the cathedral here, and that will be Professor Cyril Pennert, who is professor in cognitive and systems neuroscience at the University of Amsterdam. And the title of his talk is shown here: From the Foundations of Brain and Mind to the Computational Models and Neurotechnology. Yeah.
Thanks, Rob. The audio is okay? Yeah. And thanks for the organizers for inviting me, Noortje and congratulations to Maarten for the beautiful day, also outside, but especially for your inauguration. Very nice festive activity. Right, yeah, so as the title says, I'd like to take you through the fundamentals of neuroscience and how they speak also to the development of novel technologies, in particular to treat brain disorders, and argue that both are needed, the foundations as well as the applied side. This is our group. I work at the University of Amsterdam in the group named Cognitive and Systems Neurosciences, Rob said. And yeah, it's a very nice interdisciplinary group with computational modelers, computational people, experimentalists who mainly work on animal models. Recently also human research with brain imaging and technology branches such as optogenetics and the application to disease models. First, a little bit about the emerging field of neurotechnology. What do we have there in the range of brain disorders? Impossible to cover everything. I'd like to illustrate why we need also better fundamental understanding of brain and mind to get to better cures for instance, perception disorders or disorders of consciousness. A little bit on computer models of perception. So how are the ideas and the concepts tested by simulations and how carried on to experiments. And finally, a little bit about our work on stroke and hemi-neglect, which also happens in the context of Neurotech NL, a consortium where also people here at Eindhoven participate in. So like I said, it's very hard to give an overview of neurotechnology in general, but we do see already the emergence of very successful techniques like cochlear implants, which are applied worldwide now, and which basically rest on the insertion of electrodes into the cochlea in hearing-impaired people, where basically the hair cells are being stimulated, and then the hair cells are supposed to be intact. There's still transmission through the acoustic nerve possible, but this is widely implied in the order of hundreds of thousands of patients each year. A bit more recent development is the retinal implant, where we see the implementation of chips, light-sensitive chips, for instance, just below the retina, such that in the case of a retinal degeneration, there's still a possibility for those chips to stimulate the underlying nerve tissue, either ganglion cells which project to the brain or optic nerve. And in that way, it's still possible to give people a rough sense of central vision. Not quite the same as full-blown vision with high accuracy, but it helps to get people going again if they're threatened to become fully blind. This is also followed up in the Netherlands, for instance, by my colleague Pieter Rolfsma at the Netherlands Institute for Neuroscience, who works on the visual cortex to stimulate that part in case the eye is lost or the transmission to the brain is lost. On the lower left, you find models of epilepsy. This is work in e-brains. That's an infrastructure emerging in Europe as a follow-up to the Human Brain Project. In the work of Victor Yearsa, for instance, in Marseille, work is being done to make personalized models of epileptic brains. And these are personalized, so it means that they're specific to individuals with epilepsy. And they're able to simulate the propagation of an epileptic seizure. Once you have enough data, which is MRI scans, but also connectivity data with EEG recordings, for instance, or MEG, preferably with depth electrodes in the patient to more accurately localize the sources of electrical signals as a seizure starts to develop. This is becoming already applied to the stage where the surgeon can be advised to look for particular places assisted by this simulation technology. So, of course, the surgeon is not replaced, but advised. On the lower right, we have an instance of paralysis. Amyotrophic lateral sclerosis is being addressed by Nick Ramsey in Utrecht, for instance. But also other efforts are being made when the patient gets fully paralyzed to implant a brain-machine interface. And the idea is to record brain signals which correspond to particular willed actions of the patient, like move the cursor here and here, but also speaking. That is the derivation of electrophysiological signals from the brain, for instance, in the gamma range, that is about 40, 50 hertz oscillations, which can be translated into finger movements or in some cases even words. And then those signals are being converted with the help of algorithms into speech or like cursor movements. So that's also taking off, really. Like I said, there's an effort in Europe originating from the Human Brain Project, which drives at the establishment of a bigger digital research infrastructure across Europe, spread out across various centers with different specializations, basically to catalyze brain research. A little bit in the spirit of CERN, the particle physics accelerator in the upper right, but then not as a physics instrument, but rather as a collection of digital tools, high-performance computing, supercomputers, etc., with also a strong clinical branch. But there's a recognition that also to drive the technology forward, you need to understand better how the brain works. For that, you need to measure brain activity not only at the EEG level, that is at the scalp, the growth signals, but also at the cell level. So what are the cells doing? What is the role of interneurons of very particular cell types, which can be addressed by causal interference? For instance, optogenetics is a tool, a molecular tool by which light is used to activate or inactivate particular brain cell types, or circuits, or whole brain areas. And then computer models are needed to, basically to gauge our understanding of the process. Like Richard Feynman said, basically, in order to understand something, I have to build it, or in the case of the brain, to simulate it and then show that the concept really works. So now, other disorders are coming into view. Alzheimer's is still very difficult, a long shot. It's degeneration all over the place. Parkinson has its DBS treatment component in addition to the pharmacology. So deep brain stimulation is now also widely used. And blindness is becoming treatable. What we try to set up also for the Netherlands as a complement to the European eBrains structure is this kind of circuit in yellow-orange arrows, where we start with patient data, you supplement it with life science data, so for instance from animal models, with artificial intelligence tools, build data collections in a fair manner that is findable, accessible, interoperable, reproducible, etc., so that a lot of people across Europe and the world can work with that. Build then brain models and do simulations to validate the ideas, and hence develop that stream into neurotechnology, which is, for instance, the development of neuromorphic computing. Those are not ordinary computer chips, but rather neuron-like computing elements. So basically electronic circuits that mimic neurons, and by which you can, by doing that in parallel, you can often approximate brain functions in a way. That then leads also to the control of micro-fabricated systems, either electrodes that record brain signals, or devices to write to the brain, to manipulate brain activity, for instance by light, like I said, but also electrical stimulation, which is the standard. Here also in Eindhoven, for instance, Jury van den Burgt, but also in Twente and Groningen, a lot of people are working on the nanoscale to work with materials to make that kind of small circuit matter more intelligent. And then finally, we need to apply that to the brain. Here you have an example of the visual cortex implant of Roelfsema, where around 1,000 electrodes can be implanted to both record from brain cells, but also to stimulate. It's becoming feasible to give people that were previously totally blind with the camera a kind of rough image, but this is hopefully improving as the number of stimulation sites will increase. So a little bit about the fundamentals. If we want to eventually cure people with perceptual disorders, not particularly the man with the amputated leg over here. You also have to understand the basis of perception. I'd like to be brief about this, but basically the question here is, where is the sensation of cold water happening? The leg is artificial. There are no sensors in the foot, but still you see the man jumping up and giggling, perhaps, having this funny sensation. And also in the rotating snakes case, you might think, well, is that now, where is the rotation? Some people don't see it. I see it very much if I look at it, the spirals, especially around the point where you foveate, where your gaze is at. And yeah, is that, where is the rotation? It's a simple question, right? Maarten, do you have an answer, perhaps? Where is the rotation? Yeah, or somebody else? I should... It's made up, yeah. But where is it? Yeah, it's not on the screen, right? You can measure that. There's no physical movement on the screen, so it's not on the screen. Most people say, well, it's in the brain then, right? But it's also difficult. Just purely reasoning from materialism with, bounding every phenomenon to a place is difficult, because if a surgeon opens up the skull, he doesn't find rotating snakes in your head. At least I hope not. So rather the idea is to say, well, the brain contains the vehicle, the neurons who generate this illusory phenomenon, but it's really a representation that is neither inside the brain. It's sort of a product by the brain, if you will, projected to the outside, and that's what we experience. So here we talk a little bit about properties of conscious experience, of perception. The time is lacking to take you through all of this, but there are properties of different senses, different modalities that we experience, all very different, qualitative richness. We experience ourselves as being situated, like you sit in this room. There's not a single stimulus alone that you are aware of, but rather a stimulus in the context. And so there are properties of integration, of how you put the senses together. The ventriloquist effect, where sound and vision are also merged into a common experience, where there's a source attribution, dynamic sensibility that relates to that Necker cube, right? You can switch of how you see the cube exactly, but then the switching also has some stability, some sluggishness to it. Most importantly, interpretation is there, that we basically have a brain that doesn't generate representations of experiences of itself, but rather of something else than itself. That is called intentionality. So you do get into philosophy even. If we ask, well, how is that interpretation happening in perception? With a bunch of neurons, then one view is to say, well, basically the brain generates a copy. It just has to absorb the sensory information, and that has to code it in the way of a sort of copy form, and then you have it. But if you really look at how the nervous system works and how the brain works, we already talked about the vagus nerve, then we see that all the sensory information comes to the brain by action potentials, by electrical impulses, which pretty much look the same for all these different senses, whether it's vision or hearing. And there's no intrinsic mechanism to the brain to say, well, this action potential is about vision or about color, and the other one is about sound. So interpretation really has to happen at the level of the brain. The middle part shows a neural network, just illustrating that, what we interpret the inputs and outputs to the network to be, also in artificial intelligence, is in a way arbitrary. These are just numbers, and we can interpret the inputs and outputs, but the neural network itself cannot. So here, the upshot is really that the brain has to create its own interpretation, and a concept of simply copying the sensory information and reading it out is not working. There's an approach which goes back to Kant and Helmholtz also, that says, well, this interpretation could happen by saying that, we do not have so much direct access to world items, to real objects like the horse, but we have to infer, basically, from our sensory inputs what they are about. And this could happen roughly in the cortex, in our big giant structure below the skull, in a hierarchy of layers of cells. So there are lower visual areas, for instance, and higher. The idea here in predictive coding is that you basically create a cycling of predictions that are made by the brain. So the brain is trying to predict what causes the sensory inputs to arise. And then based on the comparison of actual input from the horse to the predictions, you can compute errors. And based on the errors, you can improve your inferences or your representations, but also learn from that. It's an idea that dates back to Helmholtz, that's 19th century, but this is now worked out in computer models, and we do our best to make them also more brain-like. So how this process of prediction works. You basically see the eye there below the brain, and the idea is that through the LGN then there's also the hierarchy in the visual cortex that does this. It's a paradigm that quickly gains adherence and support. One model is shown here by Matthias Bruchlacher in the lab. He basically built a model that says, well, can we make a model recognize a specific image of an object, but can you then also make the network recognize the identity of the object as an invariant? So you can look at the apple, it sort of rolls on, it moves on. You can recognize that it's still the same apple as it rolls on. But there's also a specific image of that would be important for grabbing the apple, actually. Those are two streams in the brain that we also need to furnish in order for things to work in our action system. And basically what it shows is that, yes, with this predictive processing schedule, you can look at the moving handwritten digit 5. It moves through the image. The picture below is a kind of distributed neural representation at a low level, so lower in the visual cortex of how that is processed. But as the image shifts, your brain cells there are different brain cells activated all the time. The propagation is to a higher area in the very high area at the bottom here, area 4. There you see that suddenly now only the same cells are being activated all the time, even though the digit is moving across the visual field. And that means that you achieve invariance. It basically means that, yes, this is a model that can sort of generatively predict what the image was, that it was a handwritten digit 5, but also that it stays constant despite the translation to the field. It also works for rotations, etc. I'm going to skip this. I'm going to end, I think, right, by briefly pointing to how we apply this kind of knowledge for neurotechnology. And that is an application built by Humberto Olcese in the lab, Erik Dijkema and Medina Husic. In an animal model, we now say, well, we basically attach a neuromorphic chip. The neuromorphic chip reads out brain signals. In this case, V1 is this lower visual area. And normally, a brain circuit in between the visual cortex and the motor circuits would mediate the conversion of visual input into motor actions. That happens, the motor actions are initiated, for instance, by ALM. Those are particular areas of the rodent for initiating, for instance, licking movements to get reward. But if an area in between is lesioned, then we try to replace it, at least partially, by this neuromorphic chip that converts read-in brain signals into stimulation patterns, writing to the brain. In that way, we hope to create not so much a brain-machine interface, but a brain-to-brain interface. And that is then taken to an animal model of hemi-neglect. This is a disorder where people, for instance, by a stroke in the right parietal cortex, lose vision for the other side, the left side of the visual field. And they cannot act on this, they cannot see it, they're often not conscious. So if you ask them, well, please bisect the lines there over there, they only do it for half of their visual field. And that's what we're trying to reproduce and restore. So I think I'd like to leave it at that. General remarks on neurotechnology to illustrate how it is emerging, but that we also need the fundamental knowledge to advance. And our approach is on this predictive processing, representationalist approaches. The advancements in computer models are important to test the ideas and to bring it further to technology. And this is then done partly by the neuromorphic chips. Thanks for your attention. Yeah.
This was a microphone as well. Yeah. We can use this for questions of the audience. Thank you for a very nice presentation.
Yeah.
There's room for some questions from the audience. Are there any? Yeah.
Thank you very much for your interesting talk. As a cell biologist by training, I see a lot of hardware used to regenerate, and Karma was telling about the regenerative medicine replacement of an in the body developed kidney. Do you think that we could also use like these in body cell-based approaches for within neurology instead of
neurology? Difficult, yeah. On the one hand, it's difficult because new cells forming, neurogenesis does happen, but not in so many places, especially not in the human brain. Another problem is, of course, to get the wiring right. This has been a traditional problem in Parkinson's disease, where people succeeded in implanting dopaminergic cells, but then to make them grow in the right direction is still a problem. But there are indeed RegMed signaling approaches where you try to guide the axon growth in the right direction. So it should certainly be pursued. Yeah, absolutely. Yeah.
Paul is,
Thank you. Well, thank you very much for an interesting talk. I was just wondering, the question is a bit philosophical in nature. Do you think that the progress of what you're doing, the modeling and the experimental psychological work that you're doing, is it going to dramatically change the classical teaching that a particular area of the human cortex is responsible for a particular interpretation or a particular perception or a particular function? Are we going to lose that completely, or do you still think that, let's say, functional neuroanatomy will stand?
Yeah, very good question, very timely question, because there are a lot of developments. One development on the cortex is to recognize how much it is interconnected. So as opposed to saying, well, visual cortex is just visual cortex because it receives the appropriate thalamic input deriving from the retina, we now recognize that about 98% of the fibers come from within the cortex. Only 2% comes from the thalamus. So the cortex primarily talks to itself, and what you see, I think, is a huge interaction. We study this by finding, for instance, auditory responsive neurons in the visual cortex. And these can be cells which do not respond to visual stimuli, but they respond to hearing. And that we interpret as a way of the modalities to interact, perhaps also in a predictive way. What you also see is a huge influence of the motor system on the sensory systems. So, for instance, we think that relates also to interpretation. So like if you make a turn with your head, then you have a particular, your brain creates an expectation of what will be out there. So it's very important to have this so-called efference copy back to the sensory systems and say, well, this is according to expectation, there's no error, or there is some surprise, and that's worth examining. So I think that's the development, to recognize a huge interaction. At the same time, I have to say, we did the optogenetics on the visual cortex and inactivated it and then tested, is that important for the rodent to detect visual change or maybe also auditory change? But only the visual change was affected. And that's classical again. So the causality is still intact. Yeah.
Okay. I think in view of time, let's thank Cyril again, and then we go to the next speaker. Thank you. Ja, die heb je straks nog nodig. Ja. So the next speaker will be Professor Evelien Carrette, who is a clinical professor at Ghent University and a clinical research coordinator at Ghent University Hospital. And, well, Evelien, the floor is yours.
Thank you very much.
Next slide should start.
Yeah. Good morning, everybody. It's a true honor for me to be here. Thank you very much for inviting me today. As Rob said, I'm part of the 4Brain research group, which is embedded in the hospital, in Ghent University Hospital at the neurology department. And today I would like to show you a part of our research, specifically to highlight our specific translational approach that we have for doing our research. And today I will show you how we have a quest for biomarkers for VNS response. But first, I would like to, I will leave it like that. I don't know how to, it's for the video, because I cannot push it, but it doesn't really matter. I would like to set the scene. What is the clinical context of our research? And our clinical context is about epilepsy. And epilepsy is one of the most common neurological diseases characterized by seizures. And a seizure is a transient occurrence of signs, symptoms that a patient has when there is excessive or synchronous neuronal activity in a certain part of the brain. And depending on what part of the brain, the symptoms can be very different. Fortunately, most of these patients are well treated with the available drugs there is on the market. About 2/3 of patients, their seizures are well treated. Nevertheless, there's 1/3 of patients who have so-called drug-resistant epilepsy, and it's very important that these, there is my video of a patient showing the seizure. So it's very important for these patients to be referred to a very specific center, a center for reference, a reference center who is helping these patients with continuing seizures. And one of the four, and the largest in Belgium, is embedded in our neurology department, is our reference center for refractory epilepsy in Ghent. And it's very important to refer these patients because the chances of a patient with drugs-resistant epilepsy to become seizure-free trying more drugs are very low. As you can see here, on this graph, the International League Against Epilepsy actually says that a patient should be considered drug-resistant as soon as he or she has tried two different drugs, because chances that they will be rendered seizure-free trying a third, a fourth, a fifth drug is very low. So patients are referred to such a specific center, such a reference center, to find out if alternatives are possible. And the highest chance for a patient to become seizure-free is actually by epilepsy surgery, where a very small part of the brain is where the seizure has its onset is being removed. However, of course, not all patients are eligible for surgery. In such a reference center, we often are performing clinical trials with new drugs that come from industry, of course, to see if this can help these patients. But if you look at this graph, we see that since the 80s, the number of compounds that are available on the market to treat epilepsy have exponentially grown. Nevertheless, the portion of patients with epilepsy who are refractory to all the compounds remains actually the same. 1/3 of patients remains refractory. So we need alternatives. And I have the honor to work at 4Brain, where we have a lot of expertise on neuromodulation as an alternative treatment for these difficult to treat patients. We could spend a whole day talking about neuromodulation for epilepsy because there's already many forms. There is a way of, as been said for Parkinson's, you can try to treat patients with intracranial deep brain stimulation, with depth electrodes or cortical electrodes. There is also a large evolvement in the extracranial way of stimulating the brain for epilepsy with transcranial magnetic stimulation, transcranial direct current stimulation, so the extracranial, and there's also new ways of delivering this stimulation. It used to be very, in a dumb way, just performing stimulation, but more and more there is research on closing the loop and really give a specific trigger at a specific timing to perform the neurostimulation. But as I said, there could be a whole symposium on this. So today I would really like to focus on a specific form of neuromodulation for epilepsy, being vagus nerve stimulation. And vagus nerve stimulation, as being already said, the vagus nerve is the wandering nerve, so the nerve that is actually wandering throughout our body. It's a cranial nerve. It has a lot of connections in the thorax, in the abdomen. It wanders through, but it also has many, many connections intracranially. And it is very easy accessible in the neck, so it It gives us the opportunity to stimulate the brain in a very wide way, broad way, via a cuff electrode that is implanted in the neck of the patient, a cuff electrode that is wounded around this wandering nerve, this vagus nerve. This is not a new technique. Worldwide, there have been 150,000 patients with epilepsy implanted with this technique. Typically, a patient is implanted by the neurosurgeon, then recovers from this surgery, and then over the weeks and months to come, the neurologist is changing the parameters and is setting the parameters straight. And it takes up to 6 months to a year to really evaluate if this treatment is efficient in a patient. So there is not an on-off situation, but there is kind of a modulation of what's happening in the brain and to have an effect on the seizures. But here you see that in 1 out of 3 of these very difficult to treat patients, we do see a very significant decrease of the seizures in the patient, more than 50%. However, in 1/3, this is less than 50%, and in 1/3, we have no effect. So this is the first group is a clear group of responders to the treatment, but we unfortunately also have quite a large number of patients who are called non-responders. And from a clinical point of view, and in our clinic, all our patients, we here see a very clear medical need. And as Maarten has said this morning, this is an identification of a problem that we need to tackle from in the clinic. And this is an example of one of the problems we want to tackle at For Brain coming from this clinical need. And these are all very specific research questions in the field of vagus nerve stimulation. Who are these patients who respond well compared to the non-responders? What is this responder profile that is so far we could not identify this? Are there biomarkers that we could set up front to say you will be a responder and you will not be a responder? What are the optimal stimulation parameters? What is the true mechanism of action? And also there's a whole field of research working on how can we make these devices smaller, less obtrusive, and so on. So for this day, I would like to focus on that and specifically show you how at For Brain we are in the very nice situation to tackle these questions in a very translational way. So as I said, we are embedded in Ghent University Hospital at the neurology department, where we of course have a lot of patients, but also a lot of infrastructure. Besides the reference center for refractory epilepsy, we are also have infrastructure where we can really monitor patients 24/7 with EEG, with video. And this gives us a great opportunity to perform our research. And as a very nice setup, we have in parallel, our preclinical lab, where we actually try to set things up very similar to what is happening in the clinic in our animal models, validated animal models for epilepsy. So we have also these video EEG set up, and for today we also have VNS work. So we also implant these rats with very small homemade electrodes to implant these in the neck of these rats, also the vagus nerve with these electrodes. We then monitor them just like we monitor our patients, the video EEG monitoring. But of course, preclinical research has its benefit because we can do more, and we can do more basic research. For instance, in this setup, we have also used microdialysis. And microdialysis is a technique where you can infuse a certain liquid in a certain part of the brain. So you implant the rat brain with a probe, you insert a certain liquid, but you can also monitor the liquid, the concentrations of neurotransmitters, for instance, in this rat brain, in that structure over time. And that is exactly what we did in a certain setup where we wanted to see what VNS does on the neurotransmitter level of a rat, and also see how this influences the seizures. So here you see the setup that I explained, the microdialysis. So you insert a liquid, and then you sample what the liquid of that part of the brain, and you see what concentrations are present. And in this setup, we had a sham-implanted group of animals and a VNS-implanted group of animals. So we monitor the concentration of the brain liquid, that's so what's happening in the brain over time. So each block is about 20 minutes. And so we collected this over time. And then in the VNS group, we started VNS stimulation. And we looked what concentration changes happened while stimulating. And then you see the P, and the P is actually the pilocarpine that is then being infused in the rat brain, and pilocarpine makes the rats having seizures. So we will also look how VNS has protected rats from seizures to occur. And what we actually saw was that when we performed this VNS, in our collections, the noradrenaline, it's a sort of neurotransmitter, the noradrenaline rose throughout by stimulating with VNS. And very much more important was that we saw that the animals that had larger increase of noradrenaline were much better protected from having seizures. So here we actually saw that noradrenaline showed who were the responders to the VNS treatment. Animals that were having a lower increase of the noradrenaline had worse seizures. So what we wanted to do in our translational approach was to see if this noradrenaline could be a biomarker in the response of our patients too. Of course, it's quite difficult to implant patients with microdialysis. So in this translational approach, we needed to find an alternative to the microdialysis, but to still show that this translation holds. And we used a so-called cognitive evoked potential because for a P300 of this cognitive evoked potential is correlated with the noradrenaline concentration in the brain. So for a cognitive evoked potential to evoke a P300, you need a so-called auditory oddball paradigm. What is this? You have to imagine that you hear tones that are very frequent, so very frequent tones, and now and then you hear an infrequent tone. So you're listening to tones, and all of a sudden there is an infrequent tone, and when you perform EEG while listening to that, your brain will react to that. And if you do this 100 times after one another, and you cut all these tiny pieces of EEG and you average them, you get to a cognitive evoked potential. And this wave that you see here, the P3 or the P300 or the peak that you see 300 milliseconds after your stimulus, that's your P3. That wave, the amplitude of it, is correlated with the noradrenaline concentration in your brain. So what we did to see if this translation holds was that we chose, in our large population of patients who have been treated long time with VNS, and we chose 10 patients that were really well responders to the VNS, so the 10 responders, and we chose 10 patients who were non-responders to the VNS. And we looked, by performing this auditory oddball paradigm, how the P3 looked like. And indeed, we saw a significant difference in our VNS responders, that they showed a larger P3 when they were in the on condition of their VNS. This is good to know. It shows that this translation holds. Nevertheless, for these patients, in a retrospective way, we already knew who was a responder and was a non-responder, so it would be much more interesting if this also holds before a VNS treatment is started, because then you could try to stratify future responders and future non-responders. And that's what we did in this second study, where we set up a prospective study. So we collected patients who would get a VNS treatment, and we followed them up for 1 year, and then looked who is a responder and a non-responder. But in the beginning, we already did our P3 experiment, and when we looked, knowing in the end what if there would be responders or non-responders, we saw that prior to VNS treatment, the P3 amplitude in the VNS off condition, so in a naive condition, was significantly different for future responders compared to non-responders. And actually in the non-responders, the amplitude was significantly higher. So this could in fact be a biomarker to, before you start VNS treatment, to already stratify patients to future responders or non-responders. In the field, there has also been a huge way of making VNS non-invasive, because of course once you implant, the implantation has been done and the patient is implanted. So there is companies and there is devices that stimulate your vagus nerve in the neck area through the skin. And in your ear, you have also a branch of your vagus nerve in the cymbal conchae of your ear. So there is also devices that are able to stimulate this branch of your vagus nerve in your ear, and this could help us to work towards prediction and biomarkers, of course. So at Ghent in Forebrain, we have we go from the bed to the bench to the bed, and I have told you all this way, but I must say that once we are in the clinic, we tend to go back to our bench, because now, for instance, we are trying to modulate the locus coeruleus, which is has a very important role in this cascade of VNS and noradrenaline release, to opto and chemogenetically try to work upon the LC to see how this influences noradrenaline release and how this influences our RADs, to maybe then get back to the clinic and to cure our patients. So thank you very much to my colleagues, but also to you for listening. Thank you very much.
Well, thank you, Evelien. Let's see if there's any questions from the audience. Anyone? Bert?
Thank you for your very beautiful presentation, your clinical experience. I think it's well established that vagal nerve stimulation has an anti-seizure effect. It has been proven in the most refractory patients. It's a last resort treatment. But what is your experience when it comes to a disease-modifying effect? What happens if you remove the electrode, stop the battery in those patients who became a responder, had at least 50% seizure reduction? It's always in discussion what it means in these patients, but what happens? Is then the effect gone, or is the disease modified?
I tend to believe the disease is not really cured or modified, because we really, the patients are being followed up, and when the battery is nearly end of life, it's very important to monitor this and to re-implant these patients. So re-implantation of the device is necessary. So to my belief, I think we modulate the way maybe the threshold is being set in the brain, but I don't think we lower the threshold low enough to then stop the stimulation for life. So I think if you're a good responder to VNS, I think it's important to keep this going. And so we also see in patients that are doing well that they suddenly do worse, and that could be due to the fact that the battery has run empty. So I rather believe it is seizure modifying, but it's not curing a patient from its epilepsy. So it's not curing the disease, I would think.
Actually, in view of time, there's not a lot of time. Let's keep your question for the coffee break. Let's thank Evelien again. Thank you.
Welcome.
And then I would like to ask the next speaker to the front, who is Dr. Jurjan Bakker, who is the Chief Technology Officer at Innovia Bioelectronics. And he will talk about, the process of bringing a device to market and what is involved in that.
Yeah? Thank you very much, Rob, for the introduction. And Maarten, good luck later today. I will not congratulate you already. I want to see it first. Thanks for the invitation. And I also want to have some time together, to talk about the triangle, because I'm not sure I'm being positioned as a representative of industry. I don't feel like that. I've been working for 10 years in Erasmus Medical Center. I'm still doing clinical research, still involved in a lot of academic science. So what is the definition of where to be in a triangle? Is it only the company or the person that's paying your salary? Let's have after a pub quiz presentation about it, or discussion. So I will try to shed a little bit of light of what it means to bring an active implantable device into the market at the end, because that's our goal, to help patients. And typically it's a long journey. And I saw from the pub quiz that 90% almost already knew the answer. So at least this talk is for the other 10%. But let's see, I will also use it a little bit as going through my CV, because it's a bit of history as well. So it's my view, it's my experience. Well, I have a little bit of conflict of interest, but most of all, I want to highlight my personal mission, and also that I developed over years. So I want to contribute to have a significant impact on a significant amount of people. And we can all debate what significant means. The first significant for me means that it's not about, with all the respect, maybe develop a drug or maybe a therapy for someone with a bit of high blood pressure. Of course, it's important, but for me, significant means working with patients, for example, with cancer, people dying, or people for which the quality of life has really reduced to almost zero. The other part, significant, means, and I know it takes a long time to come to, at the end, to a group of patients. At the beginning, in Erasmus Medical Center, we're working our beep off to treat and help a few patients, but of course, we decide to bring it to a larger group. Coming back to Erasmus. So this is my first example. In 2003, 2013, so around 10 years, I worked there with some of us I see also in the audience. Very nice. It started with a scientific idea, to treat patients with tumors in the head and neck area, with heat, with microwaves, combined with radiation, with chemotherapy. It's always a cocktail, so that's the synergy. And you saw, I just looked it up, I saw a nice paper about quite a few patients being analyzed and being published. In the meantime, there's also a company created, which is called Synergize. And I've seen on the web, so I'm just copying just the information that you can find as well, that there are now developments ongoing. And I wonder, of course, when this product development is finished and when the clinical trials start, if there's clinical trials to be done. But it will take a bit, I think, before this reaches the bigger amount of patients. So I don't know, I don't have the numbers for this case, but in my view, quite some millions have been invested from the start. 20 years of product and therapy development. It's not only about the products. To become, at the end, get your certificate for going to Europe or to the United States. So this is a little bit of the time, and time is relative, as you can see, I think, from this picture. I don't see a change. I know I lost my hair. This person here, I don't know. Did you ever had a haircut in between, or still the same? Okay. Another example, so quite busy slide, so I will try to guide you through. After my 10 years of experience in the clinic, trying to develop products for a few patients, I decided I want to have a bigger impact. I want to go to the industry at the end to develop products, hopefully in 2 years, and then go to the market and hundreds of thousands of patients benefiting for it. But I learned it took quite some more years, and also the end result was maybe not as I hoped. So on the left you can see that from Philips, basically at the time, I'm not even sure when they started, but they worked on thin film technology to make miniaturized electrodes for stimulating in the brain, but also recording in the brain. So deep brain stimulation for Parkinson is one of the patient groups that this was targeted for. And there was a startup created, a spin-off from Philips, which was called Sapiens. And I have the pleasure to work on the product development there. So what you see here is a very enlarged, but it's electronics, integrated ASICs that were placed on top of the head, very small, that were able to switch and stimulate from towards 40 electrodes in the brain. So do stimulation and recording. We tested this concept in the Amsterdam Medical Center in 8 patients, showed the benefit of having more electrodes, having the benefit of doing the recordings. And this was very successful in the sense that it raised a lot of attention. We were acquired by Medtronic, which is the biggest medical device company worldwide. And we did the integration of this technology into their platforms. And you can see me on the right, in Minneapolis in the United States, in PRL, which is a research lab for human cadavers, but also a lot of animals. Here the surgical room is empty. I'm the only one and an animal doing stimulation and recording with this equipment and this technology in a sheep, and the results were remarkable. Still, there were reasons why not to continue with this. And I will not go into much detail, but it was quite young technology, very expensive. Those leads typically have a cost price, normal leads that are implanted today, of $300. This was something that is orders of magnitude beyond. So the market, I would say, was not ready at the time. Still, the software that we developed in the time, treatment planning software, to also predict the side effects based on the MRI, based on the placement of the leads, are still being marketed. So I still have some impact, a little bit contributed to today's patient. The other example, also here in Eindhoven, is on spinal cord injury. So people that have an injury that cannot walk again, but walking is not the most important for those patients. It started way back already in preclinical research, but at least before 2008. Also in Lausanne, where Professor Ricard was doing a lot of research on rodents, later on also on monkeys, bringing that to patients at the end. So we started in 2014 to build in Eindhoven a team that is going to do the product development. And we worked there for 5 years, because it started in 2014, in Lausanne, then we moved and started in 2016 in the Netherlands. 5 years later, we developed a product platform for doing stimulation in the spinal cord, with 16 electrodes, and also in a closed loop way. So we had a body-worn device that is collecting data from, for example, motion sensors or blood pressure sensors, because at the end, this technology was more or less finished. There was an IPO, so the company went to the stock exchange to raise money, more money for bringing that product into the next phase, into the clinic. And 3 weeks ago, the first IBG, so the implantable pulse generator, was implanted in the first patient, a patient with a spinal cord injury, but not for walking, because we did already the studies that walking that works. That's nice, but it's not the most important for a large group of patients. It's about blood pressure control. So this was being announced, and this is blood pressure control where people faint basically after their injury if they stand. So they cannot sit or stand because they faint because of the blood pressure drop. And I believe this patient was already in bed for almost a year, just laying flat. Well, you can look up some of those images, or sorry, the web pages, because there's fantastic movies about mobility, people walking again, of course with crutches or with walkers, but also on the blood pressure, people standing again and making steps. All right, then something that's more for me today. I'm working for InBrain. It's a company in Barcelona. It has a daughter company which is called Inervia. Very high level. InBrain focuses on brain. Inervia focuses on nerves, peripheral nerves, vagus nerve. And we try to do a bit the same as we did before in other companies, but with a new material, which is called graphene. Maybe it's quite new still, but I think in a few years you will all find that your batteries and solar panels will contain graphene, because it is a very unique material. that was invented many years ago. A Nobel Prize has been won, by those two gentlemen in Manchester, which we collaborate with. So after this invention and after this Nobel Prize, a 1 billion project in Europe has been started in the last 10 years on a lot of projects like solar panels, electronics, battery technology, but also medical applications. And one of them is ICN2, which is a nanotechnology institute in Barcelona, and they developed this graphene into electrodes for neural interfaces, which has unique properties. Those properties and those electrodes and the preclinical use of that, for example, for epilepsy, to measure epileptic events in a very unique way with infraslow waves, has been demonstrated, and now it's the task up to industry to come up with products that can be used in humans. So what is this technology about? Well, first of all, it's a thin film technology. So it's wafer-based. It's how ASICs are being made. It's an automated process. That means no manual soldering of electrodes. As you showed an electrode, which I know is wrapped around a nerve of 0.25 millimeters diameter. Imagine you want to have an electrode array that you need to solder manually. It's impossible. So you need to go to new technologies, high-density electrodes, flexible, needs to conform to the anatomy. It's very thin. And of course, it has these graphene layers. Well, we have some indications where we target on. One of this is, again, Parkinson's disease. Why? Because the current implants are still very bulky. So big IBGs with big batteries, with wires that needs to be tunneled, that erode over time, that causes a lot of rejection of patients. And it's not very patient-centric oriented in the design. So we use those thin films, high-density electrode arrays, to at the end build thin films for cortical mapping, for tumor resection, for epileptic seizure areas, but also for deep brain stimulation. So this is an example. On the left you see today's electrode size of deep brain stimulators. There's 3 big players on the market that provide those devices. And on the right you see an impression of the sizes and the densities that we can already make today. So this is a view of how this platform could look like, because during the years we also learned that it's not only about deep brain stimulation, it's also about measuring, for example, local field potentials, but also on the cortex. It seems to be very important to close the loop for those treatment modalities. So here you see a representation of more like a cochlear device, so a small device under the skin with maybe an earpiece for processing, for wireless communication, for powering. But there's quite some challenges to do. So miniaturization, that's one. We think we can do that with those nice tiny electrodes. That also reduces a lot of less power. But this encapsulation in the body, because it needs to stay there for many years without being destroyed by the body itself, it's very important. Well, then there are things that also I know that the Technical University of Eindhoven is working on. So wireless charging, wireless communication is extremely important to make it small and efficient. Of course, the software. So last slide is these long timelines, huge amount of investments before you can make any money. At the end, also companies want to make money. So how can we accelerate this? And I think there's no single answer, so let's have a chat later on this. But it needs to come from the development, it needs to come from preclinical, also on the market approval side. I think if we all work together and closer, that means already with preclinical, maybe develop that a little bit further such that the development can take that earlier on. And also the development starts to collaborate with preclinical in early phase, start to collaborate with market approval agencies like the FDA and competent authorities in Europe. I think there's a lot to gain. And then, of course, the technology. But I think the technology is not a problem. That's it.
Okay, thank you, Jurjan. I think there could be room for one small question. Yeah, so Watt asks how much faster we could do this.
I think if you start a change now, then you will not have a gain. But I think we need to think about the future of how we do those things. So if we now work about platforms, and we can use those existing platforms that have been maybe approved for other indications, and that are versatile enough, maybe for this vagus nerve research, it can already be used. So then it depends at the end not on the platform development and on setting up companies and quality systems and the safety of the device, but to really use it for therapy development. And then maybe you still need to do a long clinical trial of, let's say, 2 years to prove not only the safety, but mostly the effectiveness of the new therapy. And I cannot really put a number, but I hope that the 20 can become 10.
Okay. Okay, then I would like to invite the speakers for the roundtable discussion. So please take seats on the chairs there.
Okay.
Yeah, so we can sit as well, Bert.
We have 10 minutes to solve this whole problem. When I first saw the network approach in functional MRI in the brain, we thought of these networks as a kind of static, invariable, topographic entities, and we know now that they are very dynamic. There's a flow of information processing, vice versa. I think the triangle cooperation is a kind of network that should be very dynamic, and maybe the whole platform idea is a kind of dynamic way of cooperating. But still, we have derived some statements here based on your work, based on your abstracts. Let's see whether we can find some steps further in cooperation. First, the academia. That's the statement for Professor Pennaerts. We know that computer models have their own life, their own truths. They can be very powerful, generating a lot of theoretical information. But is there a gap to be bridged towards clinical practice, for example? Because you want this. The first sentence in your abstract is, we want to make an impact on the life of many patients with neurological disease. Could you comment on this?
Yeah, indeed. I think there are multiple dimensions being worked on, the number of neurons, but also the cognitive capacities or functions that can be simulated, the biological realism, so how close are you actually going from artificial neural networks to more brain-like function. But yeah, if you ask about the clinic, I think one important development we see is that the models which have been largely generic can more and more incorporate details from individual patients. So that you could say, I'm not modeling epilepsy in general, but I'm taking patient X with such and such brain parameters, sizes, physiological properties of the pathways being studied, the brain areas. And then indeed, such as I briefly showed for Victor Yersa's lab, model an individual patient and make predictions of clinical usefulness. So be able to say, well, according to this model, the target of the surgeon might not be totally within hippocampal area CA3, but maybe CA1. And that can advise the surgeon to maybe modify the strategy or not. Of course, these are all subjective decisions. But I think we're going to see that personalized approach in more disease areas. Also for DBS, I think, deep brain stimulation, we see a widening into obsessive compulsive disorders, depression, and how you stimulate, where exactly and with what frequency of pulses and how strong. Also depends on biophysical modeling the tissue. And that again is sometimes very patient specific. Also for the closed loop stimulations, that could be an important development. Yeah. So the short answer is what clinical industrial interactions. Yeah, I think that the clinic can deliver all these individual patient data, and the industry can also benefit from it by incorporating it, I think. Yeah.
Dr. Bakker, Professor Carret, could you
I
add
think
some help?
indeed the personalization is possible. Also with neurostimulation, we are trying to implement that, because even a non-invasive approach of neurostimulation in a certain brain with not only structure but functional can be, you can perform the same stimulation but it's in a different brain, so it could have a different effect. So the personalization of these specific treatments, I think, is indeed quite important. And then you need, of course, a platform that is communicating with the device that is being delivered by the industry, that is allowing you that to do so.
Okay. Dr. Bakker? No? Then we proceed?
Yeah,
We-
I cannot
ample
agree
time.
more.
Okay. To the second statement, just with an eye on the clock. Well, this is something that you recognize, and in your presentation you had this whole interaction from bench to bed, which I wondered, is that deliberately, or is this the pragmatic course of events? Because you find a treatment in last resort and it seems to work. Why? You don't know. So you hunt for biomarkers then. And you are forced to go to the bench from the bed. Or is there a possibility of another more rational approach in developing more neurotechnology, not as a last resort, but as a serious treatment alternative for pharmacological treatment?
I think it's a serious alternative to pharmacological treatments, and I think I also mentioned that we should not put patients for years and years in searching for drugs, but we should take it earlier on. And I think if we would have a good strategy of defining who is the patient who would benefit the most from a more technological treatment, then this would be more accepted. And I think we already gained some years. Usually the VNS or the DBS was really very experimental kind of last resort for a patient. But I think we are getting closer. And yeah, as we are still having, not everybody seems to be a responder. So if we could indeed find the good biomarkers that we could put in, again, in a personalized way, different characteristics of a patient, for instance, the P3, but also we are looking into more to that, so that your chances of being a responder become much higher. I think you will immediately also get more acceptance for a technological therapy if you see that you implant or most responders, then your efficacy will be higher, and then I think technology, and I think it's already getting there more than in the past, will be more a treatment option early on, and not just in the end going to university hospital and doing something very experimental. No, I think, and yeah, the better we can stratify a good candidate for a certain type of neurostimulation, because I now highlighted VNS, but we have many more. And so we are actually looking for the optimal treatment for a patient as early on as possible. And the better your biomarkers are to direct a patient to the best fitting therapy will, I think, make it more accepted in the field, and it will not be a last resort anymore. That's how I think we could make some progress there.
On the computational side, then the computational neuroscience might also need to be directed more towards biomarkers. That means something in the clinic.
Yeah,
right?
indeed. Yeah, one has to move from biomarkers to causal mechanisms, I think, and see if the biomarkers are merely correlative or act as a causal factor in the process. Like you mentioned, noradrenaline in epilepsy. For which computational modeling is important. Of course, they remain models, always to be validated. But that's why interventional approaches like optogenetics are so important.
Yeah.
Again, the locus coeruleus could be an example, but there you really dissect the system causally. Yeah.
Okay.
So,
Just 2 minutes left for the third speaker, who actually dedicated his whole presentation on this statement. So I think you already answered it. But I give you the opportunity to...
Yeah, I will give one example that maybe is highlighting this, how you could do it. One of our recent collaborations is a collaboration with Merck, which is a pharmaceutical company, quite a big one. And it means that a pharmaceutical company that has a lot of drugs in the market, that understands the disease models, they're collaborating now with neuromodulation companies to look for the synergistic cocktail, basically. Similar as with oncology, where you cannot only give drugs or radiation or heat. You need to have an understanding of the disease, and you need to collaborate together. And these are really different angles. Everyone is bringing their own expertise. And if you do that early on, instead of 10 years of technology development and then bringing that to a clinical therapy development, and then maybe going back because maybe you learned that it's not working, or it has certain side effects. So doing this early on, from usually from computer models to small animal models, to larger animals, to humans, because we all know that if you bring something new into the clinic and you want to include 50 patients, it takes a lot of time and a lot of effort of everyone. So that is a very slow learning curve. So we need to find other ways to do things in parallel.
I think there's a slow approach from the neurotechnical companies to the pharmaceutical companies, the electroceutical approach, which is, I think, very hopeful.
It's hopeful, but it's a long road because these are really different worlds.
Yeah.
It's a long road. I wish to thank the audience for the participation and the excellent faculty for not only doing excellent presentation, but being in time as well, which is quite important today.
Well,
thank you all.
As I said, we would like to thank you. I'm gonna thank you with a small present from us by participating in this nice event and for this really nice discussion. Because I think that it shows really clearly why we need the triangle. And Juliana will discuss later with you where you are in the triangle. For the audience, there's time for coffee now, and I hope to see you all back at in 15 minutes on 11:15.
kut. Kun je dat ding even uit... Nee, dat hoeft helemaal niet. Dat is gewoon hier. Dat hoeft het niet, hè? Het gaat erom dat je... Je moet vooral je licht in de gaten houden. Dat is heel erg
naar de content.
Hè?
Heb je de content?
Nee, hoe bedoel je?
De PowerPoint? Ja?
Nee. Nee, dat is gewoon wat ik hier afpak, hè?
Ja, die linkse, maar die rechtse die bewoog toch niet als je die camera...
Nee,
oh,
die heb ik een plaatje van gemaakt. Je moet even slim zijn.
Werk. Hoop dat ook nog helpt. dat zat helemaal niet boven, dat zat beneden.
Een beetje geluk hebben we vandaag, komt helemaal goed.
Ik zijn we snel blij.
Hoe heet het puntje?
Is op het 8 of DX links, of ik weet niet wat er allemaal bij staat.
8.1 was het volgens mij.
8.1?
Ja, volgens mij wel. Dus voor ons gaan programmeren, maar dat kan.
Dat is wel fijn bereikbaar.
Ja, ik heb gevraagd of je gewoon een mooi patchspel kunnen doen. Klak, klak, klak.
Dat komt allemaal.
Uiteindelijk komt het een keer.
Een keer.
Ja? Zijn er weer nieuwe plannen? Of,
Ja, man. Het was allemaal zo mooi, man.
Het was allemaal zo mooi, hè, maar ja, dat klopt.
Ja, dat klopt, ja. Nog niet. Misschien boven nog even een patch inzetten.
Maar nou komt hij, ja, ga ik je even.
Oh, ja, ik ben
Ja,
wel
een handshake en zo. Dan zou die, hij zit erin. Goeie uitgang?
Ja.
Hij ziet nog niks.
Maar je ziet nog niks. Nee, met de...
Oh ja, dat is handig.
Ja, dat is wel ook wel liggen.
Ja, nog.
detail, ja.
Ja, kleinigheidje.
Ja.
Niet alles in één keer doen.
Yes, 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 yes. Kom maar, kom maar, kom maar.
Heb je al iets?
Nee. Ik heb er niks. Zo.
Kijk ik even boven, dan denk ik daar nog. 8.1 zeg je, hè?
Ja,
Ja,
van link.
ja, kijk maar naar van boven. Ja. Dat kan natuurlijk ook zijn.
Daar zitten ze daarboven waarschijnlijk met 3 man. Licht gebeurt er niks mee. Dus het enige wat je hoeft te doen is schuifjes op te zetten.
I know. Ik denk dat we voortaan dat ook gaan doen.
Ja, dan zet hij hem op het tafeltje langs. Ja.
Ik heb hem nog niet, maar optie 2 is dat ik hem daar ga afpakken. Met het very cheapo ding dat alles werkt.
Gewoon een splittertje. En dan,
En dan een lange HDMI, dat is dan wel weer een nadeel. Maar die heb ik, opticals.
als het werkt het.
Als het werkt, ja.
Ik vond hem wel fijn met die bidirectional. Werkte dat ook gewoon.
Ja, nou, met die rode kastje werkt het ook. Alleen het probleem is, als ik daar
De
rode kastje...
resolutie is dan anders. Dat het dan
Nee,
uitkomt.
resolutie is geen probleem. Het probleem is dat dan het geluid wordt geblokt door hun systeem.
Oh ja?
Ja, dus het werkt heel goed hoor. Bij mij werkt het fantastisch, alleen bij hun wordt alles weer geblokt.
Ja, maar je geluid krijg je terug van de tafel vanuit hun. Maar
Nee,
dan krijg je het geluid natuurlijk van de laptop naar...
ja, maar dat kan ik allemaal wel weer onderdrukken. Ja? Ik zie nog niks. Heb je daar niks? Dat is leuk. Dus,
Ja, soms is het ook gewoon een kabel, hè?
ja, dat is een nieuwe kabel, hè?
Cat 6 kabel, dus dit is wel een Cat 6.
Ja, maar er zit ook een Cat 6. Maar ik heb hem nog niet. Ik zal hem hier eens een keer opnieuw erin aanmelden, wie weet.
Twee jaar vindt het?
Ja, doe maar even 2, ja. Hij gaat rechtstreeks daarin boven. Gaat van boven. Hup, 2 heb ik hem. Heb ik hem. Ja, heb ik hem.
Schattig, hè? Ik kan weer slapen. Helemaal happy.
Ik ga dit gewoon vast tekenen met Japanse
Dus je gaat
lijm.
gewoon boven erin stoppen.
Gewoon, ja.
Het kastje hier beneden. Kastje
En dan werkt het.
Ja.
Maar als je dan boven gaat checken, dan wil je niet of zo.
Nee, daarboven zit niks. Dat gaat rechtstreeks hier naar die blueprint.
Ik heb memo 622 gemist dan.
Nee, dat was 722.
Die is door iedereen
Ja, vandaag. Dat was ik nog niet.
Nee, ja, het, is ook, het zijn van dit soort dingetjes die altijd... je moet het weten of... maar eigenlijk
Dat is niet zo erg, maar er zijn 7 of 5 man die het allemaal weten. Hè?
Ja.
Nee,
maar
waren
dat
niet
klopt,
hier
hè?
vandaag.
Nee, die zijn op vakantie.
Nee, die denken dat ze het weten.
Maar hij zei van gewoon aansluiten beneden werkt het.
Ja, het kastje moet beneden.
Oh, sowieso. Ja, het
Ik
kastje
dacht-
moet altijd
ik-
beneden. Dat is eigenlijk heel simpel, toch?
Ja, maar dan moet
Het
je
andere
wel...
kastje ligt op de beamer en die bekabeling die zit al.
Ja, maar dan moet je wel weten, hè, want stel
Nee,
nou-
maar hij is wel gepatcht op die andere patch. Hij zit wel gepatcht.
Dus hij zit altijd hier. Als je hem hier inprikt, werkt het eigenlijk altijd.
Ja, als je boven blijft zitten wel.
Ja, daar verandert niks aan, toch?
Ja,
Alles verandert hier.
alles wat hier niet vastgelast is, dat verandert.
Ik zeg vastlassen.
Ja, dat is echt ook
Want dit is iets, daar ga je gewoon, daar gebruik je zoveel. Je wil zo
Ja,
vaak
nee,
een,
dat is gewoon
beeldje
keimakkelijk.
van
I hope you all enjoyed your coffee. Welcome back to the second session in which we will highlight the Eindhoven MedTech Innovation Center, which was introduced by Carmen this morning. And Juriaan, I think most researchers affiliated to MTech have the same problem as you. Where do we belong in this triangle? Because it has 3 corners, but do I need to fit in a specific corner? Because the most researchers within this in MTech have multiple affiliations. So I think they all belong in the middle because they cover the whole triangle. Within this MTech session, which is called In a Heartbeat, speakers from 2 thematic topics within MTech will present their work, which is the thematic topic of cardiology and perinatology. And in both topics, everything is surrounded by the importance of a heartbeat. So I'm already looking forward to this session. And as I said, each session will start with a small pub quiz, so grab again your phones. You can probably stay in the same Mentimeter as where you were previous. Our first question is about one of an important topic within MTech is value-based healthcare. And a great example is a cardiac measurement in which functional significance of stenosis, the blockage of a vessel, can be determined with a pressure wire in the blood vessel. This is called fractional flow reserve, or FFR. But what does it mean? A, is it the ratio between the maximum achievable blood flow in a diseased coronary artery and the theoretical maximum flow in a normal coronary artery? B, the volume of blood being pumped through the vessel per unit time? C, measurement of arterial stiffness and the rate at which pressure waves move down the vessel? Or D, the sum of the isovolumic concentration and the relaxation time divided by the ejection time of the vessel? All answers probably relate to another very fancy formula within cardiology, but Marcel probably can tell everything about this. I see that the audience is doing very well because most of you gave the right answer. It's answer A. Let's go to the second question. According to the National Institute of Public Health and Environment, the RIVM of the Dutch Ministry of Health, Welfare and Sport, what is the estimated average healthcare expenses in the Netherlands per person per year in the year 2060? We all know that we are aging, so this is accompanied by an increase in our health cost. So what will it be? 7,500 euro, 10,000 euro, 12,500 euro, or 15,000 euros? And I hope we all saved money because we never know what will happen with insurance. But indeed, the estimate is that the healthcare expenses will rise up to 15,000 euro per person per year in 2060. As I said, this session is about a heartbeat, and extensive evidence is available that cardiovascular structure and functions are scaled by body size. And my question to you is, put the heartbeat rate of these organisms in the right order, going from the lowest to the fastest heartbeat. And then is the order A, B, C, D, D, C, B, A, B, C, A, or B, D, C, A. So put a heartbeat of these organisms from lowest to fastest. And I thought that we had a very well knowledgeable audience, but unfortunately in this case you all were wrong, because I can explain. The lowest heartbeat is the one of the tortoise, which is 10 beats per minute. It is followed by the heart rate of a human fetus, so answer C, with 140 beats per minute. And then there is the giraffe that only has 170 beats per minute. So it's closely resembling the human fetus. And then we have this pygmy shrew. It's a really, really tiny mouse. And its heartbeat is 1,200 beats a minute. So it's enormously high. So I was quite surprised myself that the heartbeat of the giraffe was quite comparable with a fetus if you look at scale. So I hope you enjoyed this short pop quiz again, and I would now like to give the floor to our moderators of the session, which are Carmen van Vilstre, who we already saw this morning, and Pieter Harpe from Eindhoven University of Technology. And my computer isn't working. Yeah. So the floor is yours.
Okay, thank you very much, Noortje, for the nice introduction and very good questions. So welcome. We're continuing with session 2, which has 3 talks, again trying to cover the triangle. But as Noortje already nicely put it, these 3 speakers are not at any of the corners of the triangle, but they're really in the center of it. So without further ado, let's go to our first talk. So our first speaker is Dr. Marcel van 't Veer, who is a qualified medical engineer at Catharina Hospital and also an education and research officer at the TUE. And his presentation is about Let's Beat It from Bench to Bedside. So Marcel, the floor is yours.
Thank you. Yeah, thank you, Peter, and also very nice for the invitation to be here. Indeed, I'm a bit on the edge of the triangle, and at least I have this template of the TUE, so I'm in the TUE corner. Yeah, so you just answered a question about FFR, the fractional flow reserve, and it's one of the topics that there have been many talks about. It's indeed the maximum achievable blood flow in the presence of a stenosis with respect to, say, the normal case. And it has really nice properties, because actually it was more or less from the bedside to the bench, because there was a cardiologist, Nico Peils, and he thought of this principle. And he said, well, okay, there is a linear relation between pressure and flow, so it's more or less Ohm's law. And then he came into contact with Frans van der Vossen, a professor here at biomedical engineering, and he said, it can't be that simple. The coronary arteries are much more complicated. But so they did quite a lot of research, and they found that indeed there's a really straight relation between the pressure and the flow, and it's only in certain circumstances. I also want to talk today about this really nice topic, because in about 2 weeks there's an interesting conference about temperature management, and also Maarten is going to talk over there, right? It's the 16th and 17th of June. So, but it's really interesting to see, because this it's a treatment for heart infarction, and we apply hypothermia, so we cool the heart just in the part where the infarction is, and we did quite a lot of research about it. And I could pick some other topic, because in this triangle we've a long-standing collaboration between the University of Technology here and Catherine Hospital and multiple commercial partners. But where I will talk about is a device which is used for treating cardiogenic shock. And I'll first tell you a bit about how this could develop. Mostly if people experience a cardiac infarction, they experience quite a lot of pain. So it's a lot of chest pain. And in some cases, they develop cardiogenic shock, which means that the heart, due to the fact that part of the heart is now infarcted and it can't function anymore, that the cardiac output is going down, and because of that, the nutrients to the heart itself also go down, which is a negative spiral, and then you come into cardiogenic shock, and there is no output at all, and people will die. So, really long time ago, 65 years, there was a doctor, Kentrovich, and he had a brother, he was a physicist, and they thought of a device which could be used as a cardiac assist device. And it's quite invasive, like you see over here. So the aorta is disconnected at some point, and there's a tubing around the aorta, or just on top of it in a U-shape. And this U-shape is like a tubing of your bicycle with an inner tube and outer tube. And air was pumped out and in of this tube. By doing so, the blood was sucked out of the ventricle to support the heart, and then it was inflated again, and then the blood was pumped towards the rest of the body, to your brains, and also to the heart. And it was called an intra-aortic balloon pump. And this device, like I said, has been around for a really long time. And the fact that it was like that is because before the 1980s, the treatment for myocardial infarction was just bed rest. So people who had a myocardial infarction were laid in bed and they couldn't do anything. And about 30 to 50% of the patients died. So it was a really high mortality when they had myocardial infarction. And of course, those that developed cardiogenic shock could be helped with this really invasive intra-aortic balloon pump device. But luckily, the development went on and we got thrombolysis. And thrombolysis is a drug that dissolves blood clots. And by doing so, the mortality reduced to, say, 50% of all the patients that developed myocardial infarction. And then there came PCI, percutaneous coronary intervention. And you all probably know that as Dotteren. So it's a balloon which is inflated in the coronary artery at the location where the occlusion is. And that reduced the mortality even further to 7.5%. And then stents with coating, so it's a sort of a metal tubing that was left, really further reduced the mortality. And during so, the number of people who experienced cardiogenic shock also went down. And by doing so, the use of the IBP was also going down. And it was, of course, a really interesting question to know this device, which has been around for a really long time, is it still useful for treating a patient with cardiogenic shock? And of course, the developments of this device went also further. So now it's currently it's a really small incision that you need in your groin, and then the balloon is inserted through the groin into your ascending aorta, and the balloon is just placed over there, and it's inflated when the heart is relaxed in diastole, and it's deflated when the heart is contracting. So this relatively minimal invasive device is still in use. But in 2012, there was a group who wanted to see if indeed this device would indeed has an effect on the cardiogenic shock and the reduction of mortality. And you can see over here, it's a cumulative mortality curve. I'm not sure if you are aware of these kind of things, but usually if you want to show that one has an advantage, then you want to see these curves diverging. And they were just on top of each other. So this means that in this case, the device didn't do anything for mortality. And still, of those who had cardiogenic shock, about 50% of the patients still dies. So it's still quite a high mortality. But is it still used? So I was in the cath lab once, and there was a cardiologist, and she implanted this device. And I'll show you because it's a movie, and I hope it will work. Can I push it somewhere? On. Oh, you have to do it over there. But what you will see is that I put it here in the picture. You will see the intra-aortic balloon pump. Oh no worries. I will bring back the. Oh, now it doesn't do anything anymore. Help. Yeah. And breathing rate is rising. I'm not still in cardiogenic shock, fortunately. But the thing is that you can see that it's really working. And yeah, if you want to go to the next slide, if that's possible, that's fine. So the coronary arteries can be seen, and there's a wire through it. And over the wire, there will be a stent placed, opening the artery. And this device is still supporting this patient, making the cardiac output rise and also perfusing the coronary arteries. Yeah, great. Yeah. Yeah, can I go on? Yeah, yeah. Is it? Yeah, no, it's still not working. Oh. Okay. So, like I just said, there is the fact what this intra-aortic balloon pump does. It has two main effects, and the first effect is that it increases the perfusion of the coronary arteries by inflating in diastole, and that causes the pressure to rise in diastole, yeah. No, I have it. I think yeah. Okay, great. And the other thing is that it decreases the afterload. So it's the energy that the heart needs to have to pump the blood out of the aorta. And it's represented by the lowering of the systolic pressure. And while seeing that the device is still being used, and asking about, but yeah, okay, this is theory, but how much is it? Is it 10%? Is it 50% increase in coronary blood flow? But the cardiologist couldn't answer this question. So I thought, well, okay, this is a real nice topic to do and bring it to the bench and try to think about what is indeed this effect of this IBP. So we wrote a proposal. And we had two PhD students. One was a biomedical engineer, and one was a clinician, a cardiologist in training. And we started with a model, with a lumped parameter model, representing the whole cardiovascular system. So on top, it's the pulmonary circulation. Then we have the heart, the left ventricle, with diodes as valves. We have the coronary circulation, and then the arterial circulation, the aorta, and then it goes back through the veins into the heart. And especially in the aorta, we want to implement this IBP. And we did that with time-varying parts, resistances, and inertias in compliances. By doing so, we could indeed represent the signals that we observe in the clinic. So on top you see the model, and on the bottom you see the clinical measurements. And on the left it's just the baseline aortic pressure generated by the model and also measured. And then on the right it's supported by the intra-aortic balloon pump. So in this case we could quite accurately show that the function of the IBP. And one of the things that the developer of the IBP wanted to know is how should you time it? So the inflation and deflation of the intra-aortic balloon pump. And that is what we could easily do with this model. So we could change the timing and see what the effect was on the coronary flow, on the cardiac output, and all that sort of stuff. And we had this feedback and feed forward all the time between clinics, between the development of the model, and of course also the company. In this case, it was Maquette, the developer of the IBP. And we saw that with, for instance, the deflation, this is what we predicted with our model, and this was measured in a couple of patients, and you can appreciate the same shape. But one of the things that we couldn't do in this model, or not quite easy, was making cardiogenic shock. And we went on together with LifeTech Group, which is a spin-off of the biomedical engineering department. And they have this physio heart platform. It's a slaughterhouse pig heart, which is revived in the lab, and it can replicate more or less the function of the heart of a human heart. It has more or less the same shape, and it also has the same anatomy. And what we could do in this model is to make it in cardiogenic shock by decreasing the oxygenation, and it was reversible, so we could really control the level of the cardiogenic shock. And in this case, you see that it's quite red blood, and of course, blood is red, but it's oxygenated, and when it's deoxygenated, it's almost black. It's not blue like you see in all the pictures, but it's almost black. But by doing so, we could decrease the cardiac output and control it. And what we did then, and it's quite a complex figure with a lot of information, but I will talk you through it. In the normal state, when it's oxygenated, we have a cardiac output from about 4.5 liters per minute, which is normal, with a mean arterial pressure of about 75 millimeters of mercury, and a coronary flow, which is normal, and a rather low left arterial pressure. And in this case, left arterial pressure is difficult to explain, but the lower the better. And when we made this heart fail, you can see that everything is going down the drain. And the left arterial pressure is going up, which is not a good sign. And at that point, we switched on the intra-aortic balloon pump, and instantaneously, like also the cardiologist experienced, it just revived the patient in this case. So everything normalized, or even was better than the normalization. And when we switched it off, it went back again, and then when we switched it off, it was normal again. And this was a really nice example that this device indeed really has a function. But one of the questions is, in which patient group should it still work? Because I just show you that in the normal cardiogenic shock, they did a really large randomized controlled trial, no difference. And what we observed, and that was really interesting to see, is that the coronary flow also went down. And in a normal cardiovascular system, you have your autoregulation, which causes the coronary flow to be constant. If you have, at least you have the capacity to do so. And this triggered us to do a clinical study. So we went back to the bedside again. And we did a clinical study with almost 330 patients, in patients who had a really large myocardial infarction, and randomized to get either an intra-aortic balloon pump or just normal treatment. And especially those that have ischemia still, and ischemia is represented by these parts in the ECG, is ST elevation. Normally what you would expect is that if you treat it with a PCI, Dottera, then this ST elevation would normalize. But in some cases, they still remained. And we thought, okay, in those cases, they have still ischemia, and in those patients, this autoregulation is just expired because, it's ischemia, the heart can't do anything else. So we compared that specific group, which had no or a few ST resolution after the PCI. And what we saw is that in the entire group, we indeed also saw no difference between the part where, or the group that was treated with IBP and the group that wasn't. But on the other hand, if we had this subgroup of the specific patients who had ST resolution that wasn't well, so they had still ischemia, there was a really large difference in mortality even of those patients that received an IBP. So in this case, we had our bench model giving a lot of information about this device. We understood the whole physiological model. And also, by doing so, we got the new feeling about what kind of part or what population of the patients would still benefit from this IBP. And of course, value-based healthcare, you won't use it in all patients, but we narrowed it down to a specific group that benefited from it. Like I said, I can also go on for ages and tell you about all the other cool stuff that we do, but I will just leave it here, and if you want to know about other interesting things, please let me know. Thank you very much.
Thank you, Marcel, for the very nice presentation. So we have time for a couple of questions. Yeah, Bart.
So you did a study on the timing of the device. Did you learn anything from that? Because from that you could also make it kind of patient-specific.
Yeah, exactly. So the question was, did we learn something about the timing of the device, the IBP? We did learn a lot of things because we could indeed optimize it. And in the former days, it was a task of a nurse to do so when the patient was in the ward or the CCU. It should be put, and then the doctor came and he also switched it. But eventually, it's more or less automatic. So you saw that there was a maximum, and it was really close to the R peak. So it's always ECG triggered, and if you could trigger it on the ECG, and you know when the next beat would be, and you can of course forecast that more or less, then you're quite able to do that automatically.
Thank you. Is there a second question? Yeah, Noortje.
I have a question about your cardiac platform. We did some really great experiments on that together. What I wonder, if it's an isolated heart, do you think to really translate the outcomes to a patient that you also need information from a systemic perspective? Because in patients we see that it's not only the problem with the heart, but there's mostly also a secondary effect.
Yeah, sure. So it remains a model. Model is, of course, always just a representation of a part. And that's the same case here. So one of the things is that this autoregulation is expired in this heart as well. So if you want to do the research to autoregulation, this model is not suitable. And the same holds for autoregulation like the bar reflex or whatever. But still, there's a lot of things that, we did together with the hypothermia experiments. We did biopsies and looked at the cells as well with your expertise. And I think that's a really nice platform to do so. So it has its limitations, but it also has a lot of pros.
Okay, thank you. So in view of time, let's thank Marcel once more.
Well, next speaker is already on the screen. Very brief introduction, Carola van Peul. She's a clinical physicist in the Maximum Medical Center, and both she also has a second assignment here at the Eindhoven University of Technology. Carola.
Thanks. So actually, I will start with the things my heart beats faster for. And I can tell you from personal experience that the best time of my life, actually everything is, but at least it was my pregnancy and the birth of my 2 children. And I really fully realized the wonder of this fetal development and how life is becoming from 2 cells to a small fetus with a beating heart already, a functioning nervous system. And then in the end, if everything goes well, after 9 months, your baby will be born. And after birth, this heart will adapt to this outside environment. And we will see that the heart starts beating at around 120 beats per minute. It will shift from fetal to neonatal circulation. And we see that this regulation system that regulates the heartbeat by the brain, we see already quite some development in the brain. It's not fully developed yet. And you can imagine that if premature birth happens, which means sometimes for some families, even at 24 or 25 weeks, that the fetus is not really ready for outside life. And this has consequences. And for example, the heart is not fully developed, it has to adjust faster, the brain is not fully developed, and we see that those regulation systems are not fully in place. Among, of course, other organs which are also still developing, like the lungs, etc. But we focus on these two today. And we know that premature birth in the Netherlands still quite often happens. It's about 7% of all neonatal, babies born in the Netherlands, and particularly those who are born very prematurely. So, as I said, the 24, 25-week-old babies, they have actually a lot of problems in the short and the long-term effects on health and maturation. We also know that premature infants really need care, and they are cared for usually in a neonatal intensive care unit and about an average stay of 70 days. And here's a movie of this environment. You see the incubator, you see one of those babies with mechanical or ventilation support in this case. We see all the electrodes, we see the infusion, the lines to the arms. So I wanted to show you that this environment, and it's pictured here, is really different. It's quite hostile compared to this very safe environment inside the womb. And that is what I wanted to talk about today, because we have also very beautiful moonshot projects coming, trying to get this environment much better, more in line with where the fetus is supposed to develop. But over the last years, we have been working also in this NICU situation in which we try to improve this care environment. And particularly, MMC is focused on family-centered care for about 10 years now, which means that the patients are treated in a single family room and the parents can actually be involved in the care of their baby. But you can imagine that this situation is different from an open base situation and requires advanced monitoring. And a baby, particularly a premature infant, can deteriorate very fast. So we have to detect when the heart rate slows down too much or when saturation becomes too low. And for that, we need monitoring systems. But if the patient is inside the room with the family and the nurse is not around, we need actually advanced technology to get it to, for example, a handheld of a nurse. But inside the room, we still have this monitoring. You don't hear the sound, but I can assure you it's really a lot of noise. And we have to pick up this alarm setting. And that brings me to the technology needs that we have been working on and which I'm going to tell you for the last few years. And actually, one of the focuses of our NICU was to improve this alarm management, to get fewer alarms, the silent ICU, and also to turn towards early warning. And it's not only our NICU that experiences this problem, but worldwide, over the last 10 years, alarm incidents have been reported, and it's actually a top 10 topic in healthcare as one of the main risks in particularly critical care. And also what you saw in the movie is that it's very important to go to other ways of monitoring. So we have those sticky electrodes, which is very burdensome to our infants, which have a very fragile skin. So we would like to go to a situation in which we have less obtrusive electrodes. And there's also a need for additional information to monitor the patient better. And for this, we have been working together with the university for over 30 years. So even before I started in Maximum Medical Center, already this collaboration was ongoing. And over the last 10 years, it has been expanded within MedTech. I see it as some sort of blanket over the collaboration which already was there. And Philip strengthened this collaboration by giving also force to some further developments, bringing it to clinical practice. And I will give you 3 examples today of all the other work which has been ongoing. And one of the things I mentioned before was this alarm management. And we really have a lot of alarms and also a lot of nuisance alarms. And everybody thinks that just implementing new technology helps. And it does help. But you need to optimize it and get also the human interaction and involve the humans in getting it better. So what I show you here is we did a study together with, of course, our hospital, the university, but also Philips, and not only research, but also the commercial people were involved and the business units. And what we show is that during a reference period, we measured number of alarms anyway, and we showed that implementation of a fully new system in which there is more advanced monitoring on the health visible is implemented, and we do an optimization phase also together with these groups. And we see that the number of alarms reduce, which is maybe fairly easy because you can put alarms off anyway. But we optimize it in such a way, and this is the main result, and if you want to know more, I advise you to talk to Gabriele today in the poster session. But we show actually that the green area, which is the target area for that patient group, is actually improving. So the time spent within target is much improved by 35%. So it really has a result in clinical practice, a direct result which we now already have. But of course, alarming in a late stage is actually rather stupid, right? So you would like to have something to give an alarm in advance before the patient is deteriorating or some indication. So we call that early warning. And for that, there are many illnesses, many types of deteriorations. And one of the aspects we have been focusing in our NICU, because it occurs very often, is sepsis, which is a response to an infection and is really a severe condition. And we actually developed a system in which we do further analysis of all the signals which are available but not further processed currently. And we are looking for new features which before the sepsis, which is the dark line, already show differences between a sepsis patient and a control patient. And then, of course, machine learning comes in. And we have this wonderful group with also a lot of experience from university and Philips. And we show that one of our first models was already able to get a better prediction of sepsis a few hours to 6 to 10 hours before. And in the latest results by one of our PhD students, we even get improved results. But in itself, an AUC is not everything. But what we hope to achieve is that in the upcoming few years, we will have this patient monitor, in this case the Philips one, but then there is an indicator of sepsis on top of it, real-time monitoring this sepsis upcoming and give an indication to the clinicians. Then other developments, because also this obtrusiveness of the electrodes is really burdensome. And here you see already a project which is around 2007 started by Siebrecht and our neonatologist at that time, Siddhartha Bambangatomo, together with industrial design, and they developed this smart jacket. Beautiful sensors inside a jacket instead of sticky electrodes. In the later years, we have been working on mattresses, see whether we can do it without anything on the body to detect respiration and motion. And we also developed systems or show that it's possible to monitor the respiration of infants using camera systems. And then we are interested in the motion of respiration, but also the flow signal, which we usually, if a patient is not having any adjustments like a cap for ventilation, it's hard to get this information. And I wanted to show the movie, but I don't know whether it's running. Yeah. And in the group of Sander Stuyck, together with Ilde, or PhD Ilde de Rata, showed that it's actually possible to detect this tiny flow of infants, which is giving additional information to our clinical practice. And let's see what is coming towards healthcare now. And I show you one example. And that is the smart jacket ID has actually been further developed by Siddhartha Bambangatomo together with his company. And now they're testing, and it's almost ready for clinical CE market launch. CE certification is almost granted for a Bambi belt in which we are able to monitor the patient. It has been tested in a clinical trial in our hospital, meaning that it is possible to do less obtrusive monitoring. And then one last example is the need for additional information, because there is limited information in the monitoring systems, whereas in literature you will find much more information and possible features to monitor. And one of the things we wanted to monitor is whether kangaroo care, which is known to have a beneficial effect, it increases bonding, it also has effects, good effects for the infant on long-term outcome. But we wanted to show if the effect is actually measurable. And Dede Kommers in her PhD used technology and used this sensing to detect this complex interaction between heart and brain. And we used this heart rate variability to show actually that kangaroo care has an effect. And data showed that during kangaroo care session, the heart rate variability really changes. This is just one of the parameters we can show. She also used, of course, other methods to really show that it is an improve for the infant. And the baby is better and feeling more happy inside this kangaroo care session, but also there seems to be a remaining effect afterwards, which means that we need additional information to prove that new interventions like kangaroo care, which is actually not new, right? So it's already an old-fashioned intervention, but new to do it with premature infants, to show that it helps. And if you are curious what is possible with music therapy, then also join the poster session. So I hope that I've shown you some new developments which are needed for this population in which the heart beats faster and which really improves healthcare already now. And I want to finish with saying that, here it is. This is the slide I'm supposed to talk about. With telling that my heart also still beats faster for this beautiful research, but also for the team, because I'm presenting now, but I'm presenting on behalf of the full team. So we have a full team of neonatologists, our nurses, the medical people, ICT, biomedical, the biomeds, but also our PhDs and the master students who do wonderful work, and our collaboration with other university faculty members and also Philips. And here are some names of the ones from which we show the results, but there are many others. So if your name is not on, I'm very sorry, but I'm very glad we have this collaboration. And I would like to thank my daughter for making those beautiful sketches for me. So thanks.
Thank you very much, Carole. I was wondering, because actually you can combine all these three examples you mentioned. So is that so? In what point of time you think we can see new modern care rooms where you combine all three?
Yeah, we hope to have it available soon, because but it depends, of course, on whether the companies are working together and whether the ideas are picked up by a company. Because before we can use it in medical practice, it needs to have this CE certification, which has also been talked about in this morning. So for the Bambi belt, that idea is now possible in clinical practice, and it is also it can be connected to the Philips monitor. So that is one, and we hope that new sensors will be plugged into current monitoring systems, so we can still use the equipment that we have, but use new types of sensors.
Really nice. Other questions from the audience? I did see Wart on the screen now, so you probably have no questions, Wart, because you were part of the... Other questions from other people? Well, if not, then we'll have some questions for you at the panel. Thank you very much, Carola, once more.
Very good. So with that, we move on to our third talk, presented by Professor Rick Bezemer, clinical scientist at Philips and professor, obviously, at TU Eindhoven.
Yeah,
floor is yours.
Yeah, thank you very much for the nice introduction. So Rick Bezemer, I will talk to you today about what I think is the heart of real clinical innovation, and that is actually the partnerships between the academia, the industry, and clinical centers. There's my title slide. Yeah, so that's what I will talk about. I am a clinical science leader for patient monitoring in Western Europe for Philips. And I'm also a part-time professor at the group of Massimo Mizi in the biomedical diagnostics lab. First off, setting the scene a little bit by stating that the healthcare system is under constant pressure to take care of more patients while actually reducing the amount of resources they have per patient. And this is a study conducted by the RIVM, which is part of our Dutch Ministry of Health, Welfare and Sports, to do a study based on to try to project the cost of healthcare up to 2060, based on historic data that you see here. Well, first off, they state that of course population will increase in size, also in age, on average 6 years older by 2060. They estimated, based on all sorts of models, they estimated that we will spend 290 Yeah, 290 billion euros per year on healthcare in the Netherlands alone, while that is now 80. So that makes a big difference. So they expect really a rise in healthcare costs per person. That is almost 16 actually thousand euros, while that is now 5. And 20% almost of our Dutch what is that called? Gross domestic product. So what we earn as a country, 20% of that will go to actually into healthcare again. That's quite a bit. Most costly sectors are hospital care and elderly care. And of course, the costs are not the only problem. The high demand for healthcare actually leads to long waiting lists and a high burden on the staff. And these long waiting lists, they may actually result in, of course, not so nice for the patient, but also it may lead to patient deterioration outside of the hospital, which is very nicely shown by these red people lying on the floor. The waiting list was too long. And of course, a high burnout rate and step-out rate or turnover of clinical staff. We've seen that also especially during Corona, but before that it was the same, and after that it will be also the same. So high pressure, a lot of tasks that you're not, that are in addition to the care tasks that you have, like administrative burden and whatnot. So we all feel that technology can help us improve this situation a bit. And at Philips, we talk a lot about the quadruple aim. It's basically one aim with 4 parts that are all important if you want to implement technology or solutions successfully into the clinic. First aim, of course, that was always the main aim, is to improve long-term health outcomes. An example of how technology can help to improve health outcomes is by enabling caregivers to shift from invasive surgeries towards minimally invasive surgeries by interventional X-ray, interventional ultrasound, smart catheters, stuff like that. Also important, the second part of the quadruple aim is improve patient experiences. I love this example where we partnered with Disney to create a very kid-friendly, patient-friendly or kid-friendly MR room, so they are more at ease. It's nicer for the children. Also, imaging goes better, so the quality of the images is better, and you're more productive because you go faster. Improve staff experience is an important one. One example is reduce administrative burden or intuitive visualization of clinical data. Where do you present it? Is that in the hallway? Is it on a mobile phone? And stuff like that. And ultimately, always at the end, is to reduce the overall cost of care. Cost of care is always important. One of the technological angles that we took to try to achieve that is to try to move patients sooner out of the hospital towards home, but then equip them with monitoring that allows caregivers to monitor them remotely from the hospital where the patients are at home. That would save quite some money because the patients are not all at the hospital anymore. Production can continue. And you do care coordination from the hospital towards the home setting. So a tip is when you design clinical studies to evaluate your new solution or your new technology in the clinic, make sure you not only take these health outcome measures as your primary study objectives, because actually the other 3 are just as important nowadays to get technology accepted. Actually, the main, if you ask hospital management, what are your biggest concerns? It's always the last 3, and not per se the first one, to be honest. Also, healthcare is a very interesting field to innovate in. I like this image a lot. It's 2 colleagues of mine. It's Professor Ronald Aas, also at the TUE, and Joost Kaalman sitting in the lab working on recording technology in the 80s. That was actually before I was born. And what is nice about consumer electronics and listening and working on that technology is you can evaluate quite well yourself what you expect from the technology, what customers would expect from it. You can technically measure how well it is working, and that is already the largest part of the work. While doing clinical research, it's not at all like that. You first have to understand what all these people are doing in the clinic. What are they doing? What are their tasks? What are their worries? What are the decision moments they have to take? Which decisions go bad very often, or which decisions do you make too late? If we could help you make that decision better, where would I need to present my advice to you, my clinical decision support? So really, if you do clinical research, you have to be with your feet in the clinic, talk to all these different people, and understand what they are working on, how you could help them, and iteratively come back to them and check if you're still doing the right thing. So it's at different times and a different field. So like I said, you can't judge your own work anymore. You need continuous feedback and understand the workflows and the needs. Also, and that I learned especially when I moved from Philips Research to the market organization 2019, hospital organizations are immensely complex and a lot of stakeholders, and they all want something else from technology or from solutions or from companies. And like I said, the CEO actually thinks a lot about keeping staff happy and productive and making sure the hospital is viable. But staff happiness is actually a strategic pillar for almost all hospitals that I work with, because the turnover is so high. So you spend a lot of time training people, and if they don't spend long, that's a waste. So doctors, they basically say, help me treat my patients better, detect early deterioration, predict the outcome of a certain intervention. The nurse, on the other hand, they like technology, but normally nurses have to use technology a lot to make it useful for others. So they typically state, making sure that it fits in the workflow, it shouldn't cost me too much time and effort, and then I'm happy. The patient actually wants to get home. Any solution that would help the patient get home earlier or keep him at home longer away from the hospital would be appreciated. But then you have the information officer. They said, well, all new solutions are good and well, but they have to integrate into our current platforms, current situations. It has to be backward compatible to everything we have. So bring it on. And then you have the financial officer who says, well, you can have all that, but we can only spend money on things that save us money. And that's actually, I like that quote a lot, because that's also what we as Philips have to deal with. We can only make money when we create solutions that in the end save hospital money. And then all of this, then interesting questions is always, who is now actually the customer? Who is the user? And what is the decision-making process in a hospital to decide for which technology are you going to go, for which vendor, for which partner? That is different in every hospital, and it makes it so difficult to get new solutions implemented in the clinic and also scalable towards other hospitals. And there are many more, of course, stakeholders in there. I have to hurry up. So I will skip this a little bit. Besides all the stakeholders and the complexities of a hospital and working with medical technology, and you're always liable as a doctor, so you have to make sure that whatever you try and test in the clinic is actually safe. Besides all that, it takes so much time before you get from your R&D work and your technical validation of the new solution that you have, do a clinical validation, which is very elaborate, multi-center, single-center, multi-center. Then you can finally certify your product, manufacture it, set up a sales and a support function. As an industry, you're obliged to, mandatory that when you deliver or sell a product, you can actually provide services on it for the coming, 10 years or so. So it's not just simply putting a thing on the market, it's actually making sure that the whole organization around it is adapted to that. Then you start creating clinical evidence in centers outside of your little circle. So that's, say, broader evidence. And then it can at one point be adopted in the guidelines and be reimbursed by insurance. And then people start using the technology. So it takes quite a long time. You go really deep into investments and time before you start getting the fruits from all of that. And you can have a large-scale impact. So to overcome all of this, it's important that you do not work all independently. The academia, the industry, all the clinics doing their own projects, and from the universities and the business, we throw our solutions to the hospitals that are waiting there and to see if anything sticks. No, you have to work together to speed up that innovation process and limit also a lot the wasted time that you spend on projects that were not so fruitful, and also wasted opportunities where you were not aware of each other's activities and you missed important opportunities. Everyone brings, of course, valuable parts to the table. So the clinics provide clinical guidance. There's a lot more than on this slide, of course, but what is nice is the clinic steers us at a clinical perspective, the university from a technological perspective, and the business more from a scalability perspective. Can we apply what we think now here in the Eindhoven region? Can we apply that also nationally, internationally, globally? So that brings me to closed loop innovation, a term I made up myself. I like it a lot. It basically means involve all stakeholders in the process all the time in a consortium that we created here. Looking at the foreseen hurdles that I showed in that picture with that U-shape, plot them, think about them, realize all this little stuff, like a new sensor needs to be backward and forward compatible with the patient monitoring systems that are already in the market for 6 years. So it's not easy to implement new technology in the clinic, so make sure you plan well. And work with the partners to understand what needs to be done to get it there. So that creates a win-win. You get faster innovation cycles and faster implementation of new technology or new solutions in the clinic. You waste less, and in general, you have a better return on investments for all your R&D work than you would have when you would be working alone. MedTech, of course, is an excellent example of this. Everyone is familiar with MedTech, of course. But I think it's also a unique example. So I get the question often, if Philips does this in every country and in every region. Actually, it's not. What we have here is super elaborate. Also, this whole governance structure with the data board, the IP governance team, but also daily management teams per topic. It's an old image, actually, so I'm not sure if this one is still fully 100% correct. And the amount of structural support that we put in there, all parties every year, this is a very unique collaboration. Yeah, and then I wanted to highlight two, but I see my time is up. I wanted to highlight two projects. One was nicely presented by Carola a few minutes ago. So I love that we work for these young babies and that we try to unobtrusively monitor them, to do more with the data, to make sure we to try to get to a silent NICU by better alarm management, less stress for the staff as well. And the second project, which I will summarize in one sentence, it's about ultrasound-based monitoring of hemodynamic parameters, so flow in the carotid artery of patients to provide perioperative hemodynamic or fluid management. So it's for perioperative patients. Why I like this is it's a very nice collaboration between Catharina, TUI, and Philips, because it's really about potentially a breakthrough technology where you present a new type of waveform on the patient monitor to guide clinical decision making. That hasn't happened since a very long time, like 80s or so, that you had a new waveform on there. It's really where you combine, the hardcore ultrasound engineering technologies, the adaptive AI-based algorithms for beam steering of ultrasound. It's physiological interpretation of your flow signals. So it's technology, physiology, clinical practice, all coming together. So I think it's an excellent example of what you could do in an ABC as we have here. So in conclusion, healthcare is a complex field to innovate in. ABCs, so the partnerships between academia, businesses, and clinics, lie at the center of sustainable and scalable clinical innovation and healthcare transformation. And MedTech is an excellent and unique example. I would like to thank you for your attention. And are there any questions?
Thank you very much, Rick, for your presentation and showing the, let's say, the benefits of the collaboration. It's also a nice introduction to the panel session. But before we go there, is there any question from the audience? Yep.
Yes, you said that that your work with academia and TU Eindhoven was a very nice example in this principle, but you remained qualitative. And I want to challenge you to be a little bit more quantitative, because I think these type of examples are needed to make governmental decisions whether this type of centra should be stimulated. So,
yeah.
How much matter is it?
Okay, that I don't know actually by heart, but I do find it a good point. It's important to quantify. You have the question or the answer to that, because.
The director of MedTech, I can partly at least answer your question if there's time. So in MedTech we have about 100 PhDs and about 100 staff around it. And of course the main aim is to speed up clinical innovation. That's actually hard to measure. So we measure goals. We measure the number of IP that is generated, the number of transfers of research that's going into either the product or into a new process. We measure also the amount of people that we educate, and that also end up in our ecosystem. We measure the number of publications, and they're all quite steep going up. So it's not really, so the number of PhDs is 100, I already mentioned that, and the number of publications is over 200. And if you compare that with the amount of investment, that's quite a high turnover, a high result. So that's also why this collaboration is without an end date. So everybody is committed to start every year a new program, because the results of the previous programs are quite successful. So actually we extend every year we start a new program of 4 to 5 years and extended our collaboration with another year by that.
So all the, as I may translate it, all the biomarkers are going better.
Yeah.
But the overall time from innovation
yes.
to product in do you have an answer on that?
No, we can't, to be honest, we can't measure that. So right, we just discussed that we should measure more sub-programs. What we see is that we have a very high iteration speed. In my introduction, I gave one example about the health dots. There in 2.5 years, perhaps you didn't mention it, but it was on my slide. In 2.5 years, there was, and that's much faster than in the past. So it's not yet a complete measurement from the very first start till the end, which is always quite hard to measure and has a lot of dependencies that are also outside the MedTech influence, to be honest. But within MedTech, we are able to speed up or parts of the entire innovation process, and that's we can prove. Okay, I think this brings us to the panel discussion.
Yeah.
Yeah. So thank
if
you,
we
Rick.
might invite.
Okay.
Will you join us here, Peter? Yep. Yeah. Well, actually, I want to ask the same question that just came from the audience to the other, because how did MedTech help you to speed up things? So perhaps Carola and Marcel, can you elaborate a little bit on that?
Yep. Yeah, shall I start? Or at least, yeah. Well, we have a project, and I'm not sure where they're sitting. I think they're over there. Iris and Rick. They have a comparable project that you showed about with the camera monitoring, and I think that's a really nice example where the triangle comes back into this case where both the clinics, so the question about what should be monitored, the academia, what's already feasible, and of course also Philips in this case, who wants to have this eventually into a product. And I think that it really helped, starting up the whole discussions. So that's a really tangible example of how it sped up the whole stuff.
And you, Carola?
What we see is that our IDs, and they're of course not only our IDs, so they collaborate with multiple parties, but we see IDs that we discussed with Philips before now in the patient monitoring systems or in the data systems we use at the back. So we see that the IDs are picked up in an earlier stage than would have been if we just were users and just giving those forms and give input to new developments. So it's speeding up things.
Yeah. So it's both speeding up during the development, and I think also there are less gaps between things that are finished are not putting on the shelf for 2 or 3 years. But if it's interesting, it's picked up immediately for a next project. Is that a kind of conclusion from your input?
Yeah, of course, the clinicians are always, it's always too slow because we want to have it immediately. And there's this huge process which has nothing to do with MTIC, with the medical device regulation, which slows down the things, as it has been explained by Rick. But I think we see this speeding up, that IDs are in an earlier stage going to get into the products that we use.
So your heart keeps beating fast.
Yeah, yeah.
Okay, so I'd like to move to the second question here, and that is, as Carola also mentioned in the start, MTIC is currently a local collaboration, which is very nice. You can bike there, we know each other, you can easily communicate, very gezellig. But on the longer term, would you see that this is the way to stay, or would it make sense to maybe expand to a national or even international level with this collaboration? What is your take on that?
You would like to start this time?
No, I think it's always good to have the ambition to grow, but it's important that you make sure that what you have works well. And I think that we, in the past years, we've came really to a great organization. And as you see, the whole innovation process is slow. So we haven't, maybe we've cycled it once completely. I think now we're still working on some data management things and some other infrastructural aspects. But I think, after that, certainly, so you crystallize that a bit, make sure you're stable, and then you can scale. You do that organically a bit, I would say. So one by one, maybe start with some bilateral collaborations, and then you get to trust each other, you get to know each other's organizations, and then you can scale that up. That would be my...
Yeah, thanks. I think that's a really nice approach, Carola.
I have one addition, perhaps to the AI-related research, you would need really larger databases. Yeah. So there, scaling up would really help, but there comes the difficulty with the GDPR and also the differences in data formats that are used. Mm-hmm. Yeah. And in radiology, they're much further there than we are in patient monitoring systems. So there's still work to be done, but it would be great to have bigger data sets to work with.
Yeah, but I think within the national data exchange level with Health AI, that's a national consortium already, and we are part of that as well, as the South Hub.
Yeah, so that would be a logical next step.
And what about because we mentioned now other applications and national and the triangle, what competence are we still missing in the triangle to speed things further up? What is your take about that, perhaps Marcel?
Yeah, maybe what Rick just mentioned is that in the clinics it's not necessarily always on the Netflix the quadruple aim that you mentioned. Mostly, and especially also in academia, you want to do really cool stuff and to make developments that are new. But sometimes a development that has been done and just another application would be as valuable as well. Yeah. So I think it's not necessarily that the competences are lacking, but I think that the fact that you have to talk to each other and to ask what's needed. There are a couple of examples where PhDs they need to do new stuff, especially from academia, to be able to make their publications, and it's not necessarily needed for the clinical application. Mostly just the old things that have been developed already could be applied already, and it's not a new development or new ideas or whatever, but it's a new application. So maybe what we need is that you have more focus on what's needed and more the communication about within the triangle then.
Do you agree, Carola, or do you have?
No, I fully agree there. Also implementing what is there and evaluating actually then value-based healthcare comes in. So evaluating actually what does it bring for the patient, for the people in the hospital, but also for the costs is also very important.
So you're not lacking, into your view, yet assurance companies or other kind of partners to speed things further up. There's enough. We can still improve with the current partners and with the project partners we also have, because it's not just the 5 MTech partners that are the core, but many projects, there are also other partners involved. You think it's still enough, or is there some competence or partner that you would like to add?
But maybe indeed, like you mentioned, the insurance companies, because they eventually determine what kind of budget an hospital has. I think it's really important to also, or at least to understand how this process works. Because I mentioned that the hospital is complicated, but I think the whole landscape of financing healthcare is really complicated, at least in my view. But
Okay, maybe let's move to the last question. So I think many parts have been covered there already, but if you think about 10 years from now, we have some of the ideas here, but where would you like that MTech would really stand by then? Do you have any view on that? I think I see you're already eager to answer that.
Yeah, where exactly, I don't know, but growing is good, I think, and the points that they just made about being even more, getting more value even out of the work that we already do, testing other applications. I think that way of working still needs to be a bit tighter, a bit stronger, and then I think scale up. And I don't know. It depends also on where we already have collaborations. Say each of the parties that are already on board, and then build on that to grow that consortium, I would say. Yeah.
Thanks. Carola?
I think that hopefully in 10 years we are able to show the results for also in healthcare itself, so that we can be proud of all the inventions that have already reached clinical practice. And for that, I think we need a broader collaboration also with other companies. I mentioned one other next to Philips, and I think integrating those parties. We're in a high technological area here around Eindhoven, and perhaps we should join forces even more.
Yeah, and I think maybe even also collaborating with startups, and maybe even TUE-grown, homegrown startups would be good. I think Philips could help them, give them a platform to have all of a sudden a global, say, potentially a global footprint. And we could learn a lot from the agility and from the technology from them. And I always get excited from startups and new technology and young people that want to change the world.
Marcel?
Yeah, nothing to add here, but you ask where, so it should be still in Eindhoven, right?
Yeah.
Well, if I may ask an additional question, you mentioned that it's quite unique, MTech, and it's a kind of example. So in 10 years from now, do we have MTechs branded locally in Japan and in Asia, or in the US, or what's the plan from Philips with the MTech concept?
Yeah, I think the E stands for Europe and not Eindhoven. That is in 10 years.
Okay.
Okay, very good. So I think it's time. So let's thank all of our speakers one more time.
I join Peter in thanking the speakers. Before I will show the speakers and the moderators of this session our gratitude in a small gift, I would like to thank you for your attention. There's now time for lunch, and I would point out that in the Senaatzaal there's also a poster session of PhD students that are affiliated to the Center of Care and Cure and present their work in the health domain. So please go and see the posters and start discussion on the importance of the Golden Triangle also with the PhD students, because they are the researchers for the future and really can make the impact that we are now discussing. Enjoy your lunch, and I hope to see you all back at 1:30 for our final session. Okay, welcome back everybody. I hope you enjoyed lunch and that you also had some time to look at the posters and to interact with the other people present, because that's very good, beneficial of being here in real life. For those who just joined this TU MedTech Dag, within the Center for Care and Cure we have the tradition to when we have speakers in our bi-monthly science cafe to open with a science quiz, and we decided to also start off each session with a pop quiz. So again, please pick up your phone and go to menti.com, and most of you still have the code in their screens, but the code for today is 41799139. Everybody ready? See still people trying to connect. So the first question of the pub quiz of this final session of today is about ultrasound. Certain ultrasound machines are capable of Doppler ultrasound, a special ultrasound technique that evaluates blood flow through a blood vessel, including the patient's major arteries and vein. Which of the following is not a type of Doppler ultrasound? Is it A, color Doppler, B, phase Doppler, C, power Doppler, or D, spectral Doppler? For those who just joined, I only give you the answers. If you take the answer in doubt or you have more questions, please ask them to the speakers. I see A is in favorite. Unfortunately, this is wrong. The right answer was phase Doppler. And Massimo Misci, our first speaker of this session, can tell you everything about this. Our second question, do you recognize the person in the machine? The company Synergistic, our speaker from industry today, develops the focus collar, a commercial solution based on Maarten's design of the Hypercolor 3D. How many independently controlled antennas will the focus collar provide? Is it 4, B 12, C 20, or D 48 antennas? There's quite some discussion about 20, 48. I think we all agree it's not 4. So. And the right answer is C, 20. Unfortunately, our speaker of Synergistic is not here today, but our moderator, Gerard van Roon, will step in for him. So he probably can also explain why it's 20. And our final question of this pub quiz. When treatment side effects become a problem during radiation therapy, which of the following solutions is usually offered by the doctor? A, switch the patient to chemotherapy. B, interrupt radiation therapy for a week to see if the symptoms go away and then resume with radiation therapy. C, treat the symptoms when they present and then maintain the schedule of radiation therapy. And D, change the time of the day when radiation therapy is given. Oh, now we have experts again. And indeed, the correct answer is C. And we will hear more about radiation therapy by Professor Remy Nout from the Erasmus University during his talk. This was the last pub quiz of today, and I hope you enjoyed it as much as I did by composing this pub quiz. I will now quickly give the floor to the moderators of this session, as we really have to finish at 3 o'clock, because then this room will be arranged so that Maarten can have his inaugural lecture. I would like to give the floor to the moderators of this final session of today, Gerard van Roon and Fons van der Somme.
Yes. Is it working? Welcome everybody to this session. Nice to see that there's such a big audience. I think we have an excellent set of talks in this session. The first talk will be from Professor Massimo Misci from the Department of Electrical Engineering, from the capacity group that I myself am as well, from Signal Processing System. Massimo has a broad line of research focusing on different imaging modalities, from ultrasound to MRI to electrophysiology, with a focus on understanding the full measurement chain. And if you've ever visited Massimo's office, you know that besides his excellent knowledge on science, he also has a very good taste of football. Yeah, I heard that his team just made the Conference League, so congratulations on that as well, Massimo. Massimo, the floor is yours.
Thank you. Thank you. Thanks for the invitation. It's a really great pleasure to share with you our experience developed over the years on multiparametric ultrasound and machine learning. Today we are working, in fact, on several applications of that. We are working on pancreatic cancer, we are working on uterine cancer, breast cancer. But let's say at the beginning of this journey, I was confronted with a question on which was really an application in great need for imaging technology that could also actually help. You know, in the beginning of this of a research trajectory, you need funding, so that could also help in showing the impact of such a research. So this is a journey that I made together, tightly together with clinical partners. First of all, the academic medical center. So now there I should say Amsterdam University Medical Center. At that time was the AMC in the beginning. But also the Martini Clinic in Hamburg, a leading center in Europe. And also in China, the second affiliated hospital at Zhejiang University. So asking the question, what was the application in strong need for innovation and imaging, new imaging modalities? Well, that was prostate cancer. Is the number one type of cancer in terms of incidence, and the second for mortality in men. So in strong need for diagnostic solutions that could also, in fact, support novel treatment and focal treatment, which is actually available. But still today, because of the limitations of the imaging technology, diagnostics is based on systematic biopsy. So taking 12 to 18 tissue samples from the prostate, spread over space. This is, of course, an invasive procedure. The sensitivity is not extremely high because of the fact that you are sampling in space, so you don't cover the full prostate. And also, in retrospect, because of the poor stratification of patients based on the blood test, which is the PSA, then what happens is that 3 out of 4 patients undergo, in retrospect, unnecessary biopsies, also with all the stress that comes with that. Well, nowadays we have some imaging technology that has been developed quite far and made it also to the guidelines for imaging pre-biopsy. And this is based on a number of large trials. This is MRI, so multiparametric MRI, combining different MRI modalities. However, if you look at it a bit more carefully at the data, you realize that there is a large number of false positives who still receive unnecessary biopsies, but also clinically significant prostate cancer, so the one that has a high chance of developing metastasis, is also still missed. Not to mention the poor reproducibility, especially in centers that are not expert centers. So you need really an expert center to be able to reach accurate results. And of course, we know also the limitations in relation to MRI. It's an expensive solution, and the availability is not that wide. Of course, this perhaps not such a problem in this country, but certainly in other countries. So a possible alternative to MRI that is more widely available and more cost-effective is ultrasound. What is the status of ultrasound nowadays, and which are the developments? Well, we have shear wave elastography. This is a technology that's been developed in the past years thanks also to the development of ultra-fast ultrasound, where you can generate a shear wave propagating over tissue by using a radiation force, and then if you track this shear wave and you estimate the velocity, that relates to the Young modulus of tissue. That means you can estimate the stiffness of tissue. And cancer is stiffer than benign tissue. So that helps with the diagnosis. As you see here, some of the results. Another possibility is micro-ultrasound. So if you drive your probe at very high frequencies, then you can resolve very tiny details and generate very high resolution images, which also help in the diagnosis of prostate cancer. And next to that is what we have mostly developed, is based on contrast-enhanced ultrasound, looking at the dispersion of contrast agents. So in fact, in the beginning of this journey, thinking of the use of contrast-enhanced ultrasound, so I would like to focus, in fact, on this application. We targeted the association between angiogenesis, or the development of this chaotic, irregular network of microvessels that feed the tumor, and the tumor needs it to grow beyond a few millimeters in size. We wanted to be able to detect the presence of angiogenesis, which is then would be a very strong biomarker for cancer. Well, this is supported, in fact, by a lot of literature. It's also true for prostate cancer. But, well, the difficulty is that we should be able to resolve this microvascular architecture. In particular, we wanted to really look not just at perfusion, but really try to infer which is the underlying microvascular architecture. So this, that helps us really recognizing these angiogenic networks. This received quite some funding. We were able to develop our research, and the basis of these are ultrasound contrast agents. Just to quickly tell you what that is, these are microbubbles that are injected in blood. Once they are insonified by ultrasound, they will start oscillating in a way that you can actually very nicely detect it with ultrasound, because they oscillate in a nonlinear fashion. And now what we do is to inject intravenously a bolus of ultrasound contrast agents. So you see here the prostate that is filled by these microbubbles. We extract the concentration, the evolution of the concentration of microbubbles over time and over space, so for each pixel. And then we developed our spatiotemporal analysis. This is based on a convective dispersion modeling of these microbubbles. And the idea is to extract parameters that relate to the dispersion of microbubbles in space. As you can imagine, this can, in fact, reflect the underlying microvascular architecture, which we don't see, but we can infer it by spatiotemporal analysis of the evolution of the concentration in time and space. And we developed several estimators, in fact, for dispersion over the years. And here you can see some of the results by 2D ultrasound. You see how nicely actually these dispersion maps in fact agree with the result of the histology after radical prostatectomy. Well, the next study, important study, was to be able to target biopsies based on our images. So we did that in 142 patients at the Amsterdam UMC. So this was a quite large study. And, well, here are the results. You don't have to look at all the numbers. What is important is that we compared our results to multiparametric MRI. And the detection rate, as you can see, was pretty comparable. So we detected 40 patients against 41 patients. So rather comparable if you think of the difference. And this is only one parameter. It's only based on dispersion. In general, what we observe is that, yes, the detection rate is good, is similar to multiparametric MRI, but biopsies, systematic biopsies, did still a way better. So there is room for improvement. And it was back in 2015 that we wrote this systematic review of all the possibilities that are given by ultrasound. And in fact, the major benefit that we could achieve when we could combine all this information, this complementary information, in order to boost our diagnosis. And we did the first study in collaboration with the Martini Clinic, where indeed we measured not only contrast, but also the elasticity of tissue, the standard gray level beam mode images, and combined all this information by a machine learning framework in order to see whether we could boost the diagnostic accuracy. And you can see that for clinically significant prostate cancer, we achieved quite a high receiver operating characteristic curve area. So this was very promising results. And what helped also achieving these results is being able by AI, so here we developed a deep network in order to segment the prostate also in the zones, because different zones in the prostate have different type of tissue, and that knowing that and informing the machine learning framework about this helps a lot with the classification. Then the next step was to go towards 3D. You can imagine, in 2D, if you want to measure the indicator dilution curves, then you look at the wash in and wash out of the contrast at each pixel. You can do it plane by plane. So to cover the full prostate, you need several planes and several injections. It takes a huge amount of time. So it's not feasible in a clinical workflow. But if you can scan it 3D, then you just inject the bolus and you analyze the full prostate in one go. So that's why we moved into this direction. Of course, also our models are by nature 3D models, though also helps in terms of modeling. Here you see some results of our dispersion analysis compared to the histology, and we developed this even further by developing some tractographic techniques to reconstruct the mainstreams of flow. So also these images show, in fact, quite a good agreement with the histological result. So with this technology, what we did was to develop even further into, let's say, a multi-parametric approach, but then just focusing first on ultrasound contrast agents. So we looked at dispersion parameters, that is what we developed, together with the standard perfusion parameters, combining all together, and we achieved with in a machine learning framework, again, quite nice results, even in 3D, even with these low volume rates. You can imagine ultrasound in 3D is a bit slower than in 2D. Still, we could achieve a 0.81 area under the receiver operating curve, which was very promising results. In this case, what we did was to try to predict the results of biopsies. So these were not patients referred for radical prostatectomy as before, but these are patients that just, we say, naive patients in the sense that they still, they don't know yet whether they have cancer. So, and then they receive biopsies to confirm. The next step was to develop in the direction of a full multi-parametric ultrasound approach, where we also included B-mode and elastographic information. And this was done still, again, in collaboration with a second affiliated hospital at Eindhoven University. You see here the results. Well, here you see the approach basically based on the B-mode features and the elastographic features. We had to use still 2 different scanners at that time. Now it's being all implemented in the same scanner, in fact. And the results, after combining all these parameters in the machine learning framework, we used in this case gradient boost, then were pretty promising. You see that already our QD analysis was performing very well, again confirming our previous results with a 0.81 area under the receiver characteristic curve, operating characteristic curve. Shear waves are not that excellent, but once they are combined with our QD analysis, we could boost our classification performance even further, actually to a 0.85, which is a very good result, especially when we are trying to reproduce biopsies, which is not really a perfect ground truth. So to conclude, I think, you have seen the potential of the dispersion imaging approach, the fact that expanding that to a 3D approach actually brings great advantages, especially for the clinical application. It should be multi-parametric because cancer is such a complex process that you need to use complementary parameters to help your diagnosis. And of course, more extensive validation is strongly needed and is ongoing. So we got an NIH grant now, so in collaboration with Thomas Jefferson University, we are also developing even further this technology, especially on the validation. And I think something that I would mention, and that fits very well in this meeting, is that, you could never deploy such a technique to the clinic unless you had industrial partners that are really implementing these solutions. So what we did, in fact, is that I was quite successful with a proof of concept from the ERC grant, and then we have a takeoff grant, and this year we received also EAC transition grant. So altogether helped a lot in the formation and the foundation of a startup company that is now doing pretty well and is filling the gap between research and clinical translation. For instance, the low-level implementation of our or our code, which is extremely necessary if you want really to deploy it to the clinic and therefore to patients. And also this company is now supporting very large clinical trials that will create that evidence that we need, again, to complete the clinical translation of these technologies. And with this, I'd like to thank you for your kind attention, and I like to thank especially Professor Baxter, that was my partner in all this journey, but also, of course, Professor Pintong and George Salomon from the other partners hospitals, and in particular all the students that supported and contributed to the developments that we made over the years. Thank you.
Thanks a lot, Massimo, for the nice talk. I think we have time for 1 or 2 questions before we continue. Are there any questions from the audience for Massimo? Not. Oh, yes, please.
Sorry,
if it would be applicable to other areas of the
yes,
body?
absolutely. So as I started, we are now actually working on different types of cancer, like pancreas, uterus, breast cancer. And so this technology is now being experimented also for other cancers. This is because angiogenesis is actually supporting the growth of solid tumors a bit in our organs. So it's a common process, though the features are different. So we have to learn that.
Thanks. Maybe one more question? Yes?
In your picture, it looked for the prostate, it looked like there was less signal coming back from the far end of the sensor, of the ultrasound sensor. Is that a problem, or did you take care of? Can you take care of that?
You can take care of that to a certain extent. So if you are beyond the urethra, you will face a lot of attenuation of ultrasound. So the area that is beyond the urethra, in the transition zone, is a bit less visible. On the other hand, 80% of tumors develop in the peripheral zone, which is close by. So it can be a problem, but it's not that common that you have developed tumor on that side.
Okay, thanks. Then let's thank our speaker again.
And then it's my pleasure to introduce Professor Remy Naut. He is head of the Department of Radiotherapy at Erasmus MC. And as a radiation oncologist, his passion is to improve radiotherapy, be it technical or biological, to improve radiotherapy for treatment outcome and, most importantly, also quality of life. His personal research is focused on brachytherapy in cervical cancer to increase local control, and he is part of that. He is also a leader of the international phase 3 trials.
Thank you very much, Gerard, and thank you, Maarten, also for bringing me here to this very nice symposium. Thank you. So today I will try to explain something about the work we are doing, which is much more at the beginning compared to the previous speaker of such research and development track. So this is about personalization of brachytherapy applicated for cervical cancer, and I can imagine that that is not something that the audience is very familiar with. So I try to give first a more general introduction. And in the Netherlands, we only see approximately 800, 900 cervical patients, new patients a year. But from the worldwide perspective, this is one of the most common leading causes of female cancer death. What's also important to realize is that the age at diagnosis is around 30 to 44 years is the peak. So this affects women in a period of their life that they that the treatment and diagnosis has a lot of impact, also from the socio-economical perspective. So that's important to realize. Approximately half of the patients have what we call a locally advanced cancer. And the standard treatment is a combination of external beam radiotherapy, which is given daily during approximately 5 weeks. And with that, each week, there's also a cycle of chemotherapy. And at the end, we give a treatment that's called brachytherapy. So the first part daily is external beam radiotherapy. And then at the end, we have a treatment that's called brachytherapy from brachy nearby. And that's where we give treatment using radioactive sources that are positioned close by or in the tumor. So here you see an example of a patient with a locally advanced cervical cancer at time of diagnosis, and I marked the tumor for you. And after external beam, you see that already a lot has changed. And this is an example of a patient with a good responding cancer, and you see that there's enormous volume reduction. And that's, of course, very important to take into account how a tumor also responds during treatment. Brachytherapy, I just explained, is given very nearby or in the tumor. We use applicators, and here you see an example of an applicator. And these are hollow tubes, and these are combined with what we call interstitial needles. And in these needles and in these hollow tubes, we can position a radioactive source on a guide wire. When I started my residency, which is not so long ago, we did not use MRI or the information of MRI to give this treatment, and we only had X-ray to guide our treatment. And at that moment, everyone got the same treatment, and that was a very standardized plan. Here you see a treatment plan, and these are what we call isodose lines of the brachytherapy dose. And the red line is supposed to go around this red area, which is, in this case, not so well responding tumor, where you see that the treatment that we used to give did not cover the tumor here. Over the last 2 decades, we have seen large improvements due to the introduction of MRI in the diagnostics, but also in the treatment in our field, in radiotherapy. And here you see then an example of how we treat at the moment, where we use MRI with an applicator in place, and where we also use a combination of what we call intracavitary, but also the interstitial components of an applicator to really shape the dose around the area where you want to have it, and also spare normal healthy tissue, which you also see here. Using MRI-guided treatment, we have recently demonstrated with long-term follow-up in a European collaborative study that we can achieve excellent outcomes. On the right, you see local control rates in tumors that are advanced stage 3, 4, which is excellent, around 90%. And also the overall survival is now really much better than 1-2 decades ago. But are we already there? I would say no, and it's a little bit in the small letters below, because what's really important, we can achieve really good outcome now, but we still have quite some side effects of treatment. And here we see severe side effects. That's a system for grading, and you see that approximately a quarter of the patients still suffers also severe side effects, which really impact on quality of life. And I just explained these are, on average, patients that are in a stage of life that it really has impact also on their family life and society. So there's room for improvement. And one of the areas that we think can have an impact is the way we currently use our applicators. There are limitations, and this is an illustration to show that with a very advanced commercial available applicator, we still have problems. And what we see is that an applicator has fixed positions and fixed geometry. And with that fixed geometry, you have limitations, so you cannot treat everywhere how you would want to treat. So this is a coverage problem, but also doing your best, you still also treat parts of healthy tissue with an unwanted high dose, which also gives increased risk of side effects. That's not the only point. This is a bit of a complicated slide. It's a PhD student of our department who has just recently done what we call then a time action analysis of the whole treatment procedure. And for us, on average, we have then 4 patients who undergo treatment on one day. And these are the different steps. And you can see that it's quite a complicated chaos in the department to treat these 4 patients on one day. and they have to go from the OR to the MRI to another room, and there are all kinds of steps in between that also are related to certain limitations in the whole system. And here to illustrate that, you see the time, and on average it can be around 9 hours from when the patient enters the hospital till the patient is discharged, and especially these steps in between are also related to the applicator, both the insertion and also the applicator removal before discharge. So it's really important to realize all these different aspects and all the logistics in the department that can be quite complex when you want to change something. Not only the time is important, but also, of course, the patient experience. And we have surveyed in around 100 patients patient experience in asking different important aspects on pain, anxiety, and the observed duration. And it's very good to realize what happens with the patient during such a whole treatment procedure, and also which steps. And for instance, in this case, you see that when the day passes, there is an increase also in pain and related anxiety, and especially towards the end, this also plays an important role. So these are all factors to take into account. Already some years ago, we developed a concept to look if we could make what we call them personalized applicators. So why not change this whole concept and use this imaging information that we have to really design a patient-specific applicator, taking into account also the anatomy of that individual patient. And this is the first actual device we made in a very simple way, where we filled the vaginal cavity with ultrasound gel during the MRI, and we used that shape to design a 3D printed applicator, and we made patient-specific spaces to position the interstitial needles in. That was the onset for us to start a project which we call the Architect project, in which the goal is at the end to make these 3D printed applicators in a more, I would say, more robust way, where we also use the 3D information from the MRI to more optimally space these needles. And the procedure that we follow is that we use the MRI, we contour the areas, we have to delineate that, and then we use the surface design to make the model. But what's important also is how we position these needles in space. So another PhD student started working on this, and as part of his thesis, he used different methods to explore how to plan these needle trajectories. When you start with such a project, for me as a clinician, it has been really crucial to collaborate with a technical university and to learn from the technical university side all these different aspects. And the challenge here is not only to make something that can overcome more geometric obstacles, but also to take into account dosimetric aspects from radiation. So it's a combination of different fields that have to come together in order to optimize such a problem. And in the thesis, this was done in a 2D way, but we are now making this software to do that automatic in 3D. Another aspect that we also looked at, here you see an example of such a source on a guide wire, a radioactive source, that goes through a standard ring applicator. And what's very important is the limitations of such guide wires inside hollow tubes. And even deviations of around 1-2 millimeters can have quite some effect given the strong dose gradients that we have. And the problem, or one of the challenges with a personalized applicator, is that also each applicator will have a different positioning of these hollow tubes. So in order to do this and to design this in a good way, we investigated if we can also simulate this based on information of the guide wires. What we then did was use data to simulate that. And this is the work that has just also been presented at our conference. And what you can see is, if you know information on friction and forces of these cables in such hollow spaces, you can actually use this information to simulate this in a very good way. So to summarize, I think in this field where we're working, there's plenty of opportunities, in this case to decrease side effects and treatment burden and to improve tumor control. And I think we just saw some examples where it's really crucial that we have a good collaboration with partners in academia, in our case, a medical hospital, with a technical university, but also with industry. And I think that is really crucial. We also have quite some challenges, and I think you have already discussed MDR today, but also from the clinical perspective, logistics, time pass, clinical studies, it's not easy to get everything together at the right moment. And we just saw some first, let's say, technical challenges that we are encountering on this project, such as source path planning and brachytherapy workflow, and all that is needed for such an applicator where you have a very short period in time to design and produce such a device. And we didn't touch material and printing, but all kinds of aspects come together in such a project. That is almost my last slide, Gerard. I just want to acknowledge everyone that is also collaborating on this project, and also briefly just want to thank Maarten specifically, because Maarten has been working at our department already for many years, and we have had a very successful collaboration. So I just want to thank Maarten specifically now also for all these years of good collaboration with our department, and we look forward to collaborating further in the future. Thank you.
Remy, for a very interesting talk and also pointing out a number of challenges. Any questions from the audience? Yes, please. Oh, we have this throw, he can catch it.
Thank you. So I'm very happy to see that hypothermia is now regularly used in this clinical practice. My question is, for the brachytherapy, are you also combining that with hypothermia or not?
Yeah, that's a very good question. Classically, hypothermia is given as a separate treatment, usually during external beam, and it's given on a weekly basis. Gerard has a project at our department where we have actually designed these needles to be able to also, if you have, let's say, several needles, then you can also use that as antennas to perform hypothermia. So this is really, I would say, but Gerard can talk more about that at the moment in the preclinical, but well, near to going to clinical steps, I would say. But this is not done in routine clinic yet.
Okay. So we go overguard, we're going to test it.
Yeah. But I think it's interesting, especially, for instance, in recurrent tumors. Yeah.
Any more questions? If not, and there is still time, I would like to ask a question myself, because we have been discussing a lot about evidence-based. I mean, the whole clinical decisions are made on evidence-based systems. You showed very nicely response rates of 75% or higher. I think 75% was even on the lower side. If you're going to improve your system, would your focus be on reduced toxicity? I think you also indicated that, or improved control?
I think it's a really good question. There are two aspects, I think. But what I just showed is indeed that at the moment we already have quite good results, and the focus should really be on decreasing morbidity. And I think that is also the benefit that we can more easily actually demonstrate. But there are also a lot of challenges in clinical trials in demonstrating benefits in morbidity. But we have also very good examples where benefits in morbidity have been demonstrated in clinical trials, also leading to practice-changing results.
I think that's nice, but also for the audience. Oh, sorry. Oh, thank you. Please, we can continue this discussion later also in
Regarding the morbidity, I think morbidity is also a personal experience. So each patient reacts differently on chemotherapy or on another treatment, and also how they experience the severity of their therapy. So how is it? Can you adapt that in a sort of a personalized treatment to lower down personalized experienced morbidity? Maybe.
So two things. We also use patient-reported outcomes to measure observed morbidity as side effects. And of course, it's challenging on an individual basis to let's say have a solid, let's say evidence-based decision making on a very individualized basis. But what is important, I think, is to use these patient-reported outcomes also to inform patients in a good as possible manner about what they can expect. And of course, these are averages over many patients. And you're right, we also know from patient-reported outcome studies that personality, for instance, there are all types of aspects that affect how people observe their treatment and side effects. So there's always a challenge of having evidence from a population and translating it into an individual, individualized aspect.
I think there's still time.
Because Jan Dijkendijk is sitting here. He's the proponent for MR-Linac. How do you see the relation between, let's say, your treatment and the MR-Linac? How does that go in future? What do you think?
I think that at the moment, I would say with brachytherapy, we are still able to give at the moment a steeper dose gradient, which has some intrinsic benefit over what we can achieve with an external linear accelerator. Jan might disagree, but that's my opinion. And there are certain challenges, I think, on both sides. And one of the advantages of brachytherapy is that such an applicator is very fixed inside the target area. And with an external device, you still have there is certain uncertainty with regard to exact positioning. Of course, on both sides there are limitations and benefits. But at the moment, if you look at the evidence that we have, there's a clear evidence that there is an overall survival advantage of brachytherapy compared to external beam radiotherapy. Of course, you can also argue that most of that data is not done on an MR-Linac. So I think we will see in the future how this pans out. Yeah.
And combination of the two?
Well, that's also a very interesting, I think, way to think. But at the moment, we still use quite a fractionated schedule over time. So there are some, let's say, logistical challenges. If you would really hypofractionate your first part of external beam radiotherapy, then I think there would be, probably it would be more practical. But I think Jan would be able to say much more about that. But I can imagine that having these patients coming 5 days a week on such a machine for 5 weeks, it depends on how many patients you treat, but in our situation, we would need a lot of machines.
But luckily also, that was not the topic, MR Linux of this talk. So we delay that discussion till later after the coffee, or in the coffee break, and then we will continue. We'll see. Thank you so far for your great presentation, and we continue with the next presentation, and yeah. Now I should have to introduce myself, because unfortunately the speaker, the original speaker, Paul van der Biegelaar, is not able to be here. He, I think I can disclose that. He tested positively this morning, and he said, I will come, but I said, no, for the protection of the audience, we rather have you to stay home, and it was not feasible to do it in Teams. So I have volunteered to give his presentation, but you have to forgive me that I didn't know upfront what his talk would be. So I have to look to the written presentation, and I will do it as good as possible. I cannot answer for him, but you're still free to bring up questions later on, and I will try to answer them also as good as I can. But that's it. Or if you say you want to have coffee earlier, 15 minutes, that's also an option, of course. So, but let me start with introducing Paul van der Biegelaar. He has been an executive, or he has more than 30 years of experience in high-tech medicine, of which 15 years as an executive. And his latest experience was with Nucleotron, the company that sold, a Dutch famous company that sold the brachytherapy devices and was a world leader, is now with Elekta. And currently, Paul van der Biegelaar is the Chief Executive Officer of Synergistic BV, our startup company aiming at introducing a breakthrough technology for thermotherapy. And this is the device. No, because I see one further than you. So you see the device here on your screen. This is the new device of the head and neck hypothermia. And companies, his title is Companies. Where is it here? Companies and clinical research. Is it a marriage of love? And yeah, his aim was today to talk to you about the relationship between companies and clinical research. And it's not always an harmonious marriage, as we know. Let's see why and if it can be done differently. So, the first slide is already there. I have to keep looking to there. So on this MedTech Day, we speak about medical technology development. It always starts with a physician with an unmet need and a situation in his or her practice that needs improvement. Either the physician invents that improvement himself. What's happening now? Yeah. Or he turns to a technical researcher who provides him with a solution, because that is what engineers are about, finding solutions. It also happens in the other direction. In either case, there is a need and a solution that meet to start a true development. So are you developing, as an engineer, you can develop a system and then try to find a disease, or in this case, I think that's also what he wants to say, is do you have a real clinical need, and do you find a solution for that? And of course, it's clear that a device starting from a clinical need has a higher opportunity to bring it to success than vice versa. So the key questions that you put on a system is whether it's safe or it's effective. And once this combination of problem and solution is made, there are a few key questions that come up. And everybody is aware of the risk of new technology. The first question is the safety, obviously immediately followed by the question of efficacy. If either one of these questions is negative, it's a definitively a no-go. The design goes in the bin and you go back to the drawing board. But thanks to smart researchers, I have to see, because sometimes I think I have, it says here click, and I see nothing happening there. But let's see, yes, something happened, it's very small. It's the yes. Thanks to smart researchers and engineers, as educated as, for instance, at the TU Eindhoven, many times the answer is positive. But is that enough? I would argue not at all. The whole concept of new solution to an unmet clinical need is absolutely worthless if it cannot reach patients all over the world. We hear so much about great new discoveries made in a research clinic, but exclusivity of such discovery for only patients treated at that clinic does not make this invention an innovation. The work of inventing physicians, researchers and engineers is of no value if it does not reach a large population of patients in need for such an invention. So if we can say yes every time and reach patients worldwide, do we have an effective innovation? Have we contributed to the Millennium Goals of the United Nations to combat diseases? Wait a minute. Let's first evaluate how we can now know this yes is truly a positive answer to the questions. There needs to be sufficient evidence that it is acceptable for the larger world, not only other physicians, but more importantly patients, and also healthcare payers. Insurance companies and government authorities want to be convinced it is safe, effective, and should be provided to the patients worldwide at affordable cost. I think this is speaking for itself. You need to have to fulfill all those criteria. Over time, the different parties that have a role in evaluating this yes have come up with a set of guidelines on how to evaluate efficacy and safety. Unfortunately, these are guidelines and it is not a set of fixed rules. So there is an ongoing argument about these steps. Particularly, as you can see, they are not too easy to implement. It takes a lot of patience to pass all tests. Questions of the impact of side effects versus the benefit of the treatment are not always easy to answer, specifically in oncology. Radiotherapy and chemotherapy are inherently toxic for patients, but still it is considered at this moment one of the best treatment modalities. Also, the comparison to standard treatment is not easy to make, since standard treatment is constantly evolving, and so by the time the evolution is finished, the standard of care has moved on. So he didn't discuss the necessity of randomized trials, but if you do normally a proof of efficacy, you start with a phase 0 trial. You need a low amount of patients, and you can decide whether the device is that at low dose there is no harm, And if you go to the next steps, side effects and efficacy, the number of patients that you need in your trial are increasing, and you go from a single-arm trial to a randomized trial if you want to compare your treatments, your novel, your innovative treatment, compared to the standard treatment. And more undefined is long-term benefits and side effects. They are often not randomized, often also retrospective. But overall, it may not surprise you that literature shows that in medical technology, 50% of all the evidence leads to a no. And that's there. High risk instead of a yes. For an academic setting, the price of failure may unbearably high. So if you go all these steps, if you have only a chance, a probability of 1 out of 2 that you will pass these steps. So let's go back to our starting point: a physician with an unmet need and a technical researcher with a high potential technology. They are faced with creation of evidence that needs to meet high standards and with the high risk of failure, which is costly when this happens in the later stages of evidence-based. And if all evidence is provided, they still need to reach the larger world outside their own clinic or research institute. The starting point is evidently inadequate to achieve all of the goals of an innovation. Then comes the entrepreneur. If we want to accomplish something with medical technology improvements, entrepreneurs are key contributors in this process. His message to all researchers and clinicians gather here today: make us part of your team to become truly effective. And I realize this is easier said than done. And so, we have heard this morning, cost of 100 million for making it to the clinic. So you're facing really challenges if you want to bring your medical technological development to the patients. Where the dialogue between the physician and the technical researcher is not always easy, in the end, and they usually do come to an understanding of each other, both in their drive to create something new and solve an important problem. Such a dialogue is usually far more intensive when an entrepreneur is starting to invest his or her resources. So it's too expensive, scientifically not interesting, or in larger studies, focus, speed, and quality are our drivers. Stick to the protocol. This patient needs special attention, but sometimes this conflicts with attentions for the patients. Sometimes you cannot include all your patients that you want, or you have to be more relaxed on you have to be more relaxed on your exclusion criteria and the scientific objective of researchers. It is not easy to make this an effective dialogue, let alone a happy marriage. So I think these are the cons, and here you see reasons why we should relieve a little bit more on those restrictions. And especially if you are in a niche, the number of patients are not that large, so you need to be very inventive, but also very strict on doing this. Now let's look at how it can be done differently by a live example, particularly relevant for the occasion. Our starting point was a physician with an unmet need and a technical researcher with a high potential technology. So the physician is on the left. This physician was the late Professor Levendag, head of the Daniel den Hoek clinic in Rotterdam. As a head and neck specialist with radiation oncology, he was struggling to find a better outcome for his patients. He was aware of the reputation of his institute, built now comes a sentence that is difficult for me to pronounce, built on the work of me, today your moderator, in heating tumors. But for head and neck, he found it absolutely unacceptable to use this method. That's true. At that time, the state of the technology was to put in some energy and hope for the best, essentially blind heating. I always mentioned it, dump and pray. So I responded to this challenge with this high technology, with this high potential technology via phased array microwaves and image guidance. And yeah, then this person comes in that you see now, because yeah, by that time, 1982, I was made aware by Anton Tijhuis, he is also here in the audience, that there was a smart Master of Science student just graduated. Well, he was still doing his master thesis, and based upon that master thesis, we were able to write a grant application with the Dutch Cancer Society, which was granted, and based upon that granted study, we hired Maarten to work on the head and neck applicator. And he aspired to build a device that was safe, effective, and Maarten aspired to build a device that was safe, effective, and could benefit patients worldwide. And he also dared to go into the system himself. And what it is about, he will explain himself by the movie. Now let's see whether this goes correctly.
Steer the heat to the tumor while avoiding sensitive organs
like
eyes, brain and spinal cord. The hypercolor 3D consists of two semicircular shells which are placed around the tumor area. The shells contain 20 antennas to accurately focus the heat. In addition, we developed new software to adapt the treatment. Prior agreed treatment goals put physicians in control. In this way, a novel clinical procedure ensures precise and consistent modeling for optimizing the heat delivery to the patient.
So, now you know all about the technology, but then, as an entrepreneur, he could not, Paul van der Billen could not walk away from this invention, and with his partners, Peter van Paassen, me, and also Maarten, we founded Synergistic once Erasmus wanted to grant us a license on the IP and the technology. But then we realized we each could not go our own way after this first step. As soon as Synergistic raised its first funding, we provided at several occasions research sponsorships to Erasmus, who was then capable of completing a first clinical study that contributed to the recognition of a yes in the set of key questions towards the ultimate goal. Therefore, it was obvious we as a company need to take the next step, which is both the sponsorship of a PhD student, as well as enabling Erasmus to bring their excellence outside Erasmus to all clinics who are eager to advance this development. So be a center of excellence and make a European network. Eventually, Erasmus can take the lead in an international clinical study that will lead to broad adoption of the work that started with an unmet need from a physician, a promising technology from a researcher, and a bright young man that made it happen. So the key takeaways are shown here. And on the question of collaboration between research and companies, it is obvious they must work together. One cannot work without the other, but they need to recognize this ahead of to recognize this ahead of time in an open and transparent communication to make sure there is a mutual agreed objective regardless of the differences in the background. A second takeaway for us at Synergistic is that Maarten and the entire team at Erasmus MC have done an excellent job in their work at the Hypercolor and the Hypercolor 3D, and we look forward to an extended period of intense collaboration to make this truly an important step forward for patients with head and neck cancer. Thank you for your attention. So I'm sorry that I hesitated some here and there, but that was due to the lack of synchronization between the reading and the pictures. Any questions on this?
Question from Carmen. There you go.
Yeah, thank you for doing this improviserende effort. Thank you very much. I was wondering, how far is this product now on the market? Is it already in the market as a CE-approved product, or what's the status?
That would have been great if we were that far, but that's not the case at this moment. So it's we are in the process of acquiring the funds, and that is really looking very promising at this moment. And we are working with industry to build the system and to make the first prototypes available within the next 1.5 to 2 years.
Okay, thanks.
And based upon the current results, we already started with the collaboration with Erasmus. Say we are currently preparing with the prototype device a phase 1 study in primary cancer, in patients with primary cancer. At this moment, we applied the system with patients with recurrent cancer in previously irradiated areas, but the next step is then to go to primary patients.
More questions? Otherwise, in view of time, maybe good to move to the panel discussion. Yeah.
Yep.
Noortje, will you advance the slides?
So I'm not sure who I am. Am I Paul van der Biggelaar or am I the moderator? So one part is sitting there and one part is sitting here. So let's see. What we put down here is that the time for idea to product is currently very long. During this time, risks can emerge that render the final product suboptimal or even obsolete. Think about an adjusted medical standard or improved artificial intelligence technique. So the question is, how can we expedite this process to ensure these valuable techniques to not succumb before reaching the finish line? I think this applies both for your diagnostic device as it is for hypothermia. So would you like to respond?
Yeah, it's okay. Well, yeah, indeed, in our case, it took indeed quite long to the time we are now, and which is not the end. The idea was actually 2007, so you can imagine how long it took. If you think in terms of how to speed up this process, I think one of the tips that was in the presentation you gave on behalf, I think one is there, so to really build a partnership with an industrial partner a bit earlier along the way. This is not always possible because if you have a very innovative idea, sometimes for instance, for large companies, this may be complicated. That doesn't fit. So this long-term research, it will be long-term anyway. It doesn't fit maybe a shorter-term roadmap in many cases. So in that cases, if that is the case, well, the solution could be maybe to try to join a bit later in this process, or perhaps what we did is actually to try to establish a startup company that is actually taking care of all the other aspects that are not purely scientific aspects. And there are so many. And in particular, the gap that I experience in all our research, actually, that comes between the codes that we develop, well, we are at the Signal Process Systems group, which are usually written at high level, and the code that is required for an industrial implementation, which is typically low level. Or who is generating this professional code? It's not something we can ask our PhD, so you really need an industrial partner for doing that.
Yes.
Maybe to follow up on that, so you work also a lot with AI, and so what I've seen is that sometimes when you want to get clinical approval, even if you work with industry, that can take a couple of years even before you have gathered all the evidence that it's actually working. And that refers to the part on AI, right? So maybe the techniques may change, and then you don't, if you, for instance, have a better model, but it's just doing a better job, but it's approximately the same, you don't want to start that trial all over again. Do you have any ideas to how we could do that in a better way so that we can have always the best AI technique available and not the one from 5 years ago?
Yeah, I think there should be a framework in place where you have an acceleration of innovation, and this applies to the MDR or to the ethical approvals for the studies for everything. You have seen that we have often collaborated with Chinese partners. So there in China, all this process is in fact much faster. Well, safety of patients is of course key and should be actually the leading point. But do we think that in China, for instance, safety is not so much taken into account? Well, I doubt, because I know how demanding are Chinese patients, for instance, compared even to Dutch patients. So I think it's really a matter of finding a way to accelerate the process and not start the process all over each time that you have a minor innovation. It should be a framework where you can add innovation to innovation in a faster way. I think some of the hospitals also in the Netherlands, especially for ethical approval, they have some larger framework that comprise a large set of researches and type of research that can actually fall under this kind of agreement, and so as to have approval, but much faster.
But they do. So I also would like to give Remy the opportunity to say something. But before I do so, I also want to respond briefly on your comments. Is that if you have to bring in a startup at the right time, I think, because we as Sensis, we noted that we were sometimes too large for the handkerchief, but too small for the for the
sheet.
For the sheet. So if you are, what I want to say is that if you are within your startup, if you are moving faster than what is available on the market at that time, you are not received by either the investor at the very initial point, and you're not interesting for the one that is closer to the market. And that brings also an additional challenge. And for that, I would like to go to Remy. I mean, with your 3D printed, I mean, it's a simple, making it is relatively simple. Bringing, at least that's my idea, but maybe I'm wrong. So how is that going with your innovation?
Yeah, so maybe first just one additional point, I think, to the previous discussion, because I think what we see now more and more, but I think we can still improve on that, is how we have open source results and data available. Because I think that if you store, if you have a good access to stored previous results, that can be a way, at least, to access raw data and with new methods, again, also bring some form of acceleration. Of course, you cannot do everything, so certain steps, of course, you cannot reproduce by looking at historical data. But there's something in that. And Gerard, for your question, I think that well, we are in the lucky position to collaborate in this case with an already established company. And I think in the Netherlands we can be quite lucky that we have these grant opportunities, for instance, from NWO KWF with public-private partnership, that in a way also force you to work with an established company, because they need to bring in substantial funding. And of course, having the collaboration with an established company is of great benefit in these steps, because there is experience with bringing products to the market, and a certain scrutiny from the company perspective that you also need. So I think that's of course a benefit compared to starting up a company in a novel area. I think that's even more challenging.
So we have two minutes. You go for the third question.
Let's go for the next. Which one is? Yeah, maybe this is one that I am especially interested in. maybe it holds for both of you. It's not exclusively for AI research, but in AI research it occurs a lot now, right? We need a lot of patient data to develop these models, and then we start out under the academic umbrella, and patients give their data for free, and we can do some research and show that actually sometimes AI can really help drive clinical innovation and actually make doctors, allow them to make better prediction. But then if this will result in a spin-off, this technology is sold, and then of course the hospitals have to pay for this. This ends up at the insurance, and they have to raise their interest for the actual customers, like the patients. So yeah, we were wondering, is the patient now paying double, both in data and in increased healthcare costs for these methods? And could we address that in some way?
Well, in many cases, the fact that you get some innovative technology reimbursed means that overall there is some saving, because it's very difficult to actually bring to the market and implement in a clinic something that will cost more than what you pay now. So overall, there is a health technology assessment that is intended to show that your technology will lead to some savings.
And still in healthcare costs have been increasing only, right?
That is true, probably not so much because of innovation, but for many factors, I think, especially chronic diseases and the increased age expectations, and all these factors contribute a lot. But I think innovation and what we try to bring in is something that will actually allow saving more rather than spending more.
Yeah, so that's the story we can pitch to the patients that provide their data for free, that in the end, it leads to more efficient and better healthcare costs for the same price.
I think so.
Okay.
I would add to that. I think that we should not only look, of course, we should look at costs, but it's not only about costs, it's about benefit to the patient. So for the patient perspective, it is always about, let's say, giving data or helping research for the motivation to help future patients. So in that way, of course, I mean, it's a good point, but I think that that the balance has another factor, and that is, of course, the incremental benefit if a new treatment or a new AI method is really bringing a better outcome, then it is for generations of benefit, which easily outweighs these aspects.
I think that's a good point to conclude with. Right?
Yes, thank you.
Okay, then thanks all for your attention. I think we have a coffee break now, Noortje, or not? No. Or we continue directly? Oh, sorry.
It's almost time for coffee. I would like to thank the speakers and the moderators for their contribution to this session, and I would like an extra warm applause for Gerard to be here out of the blue presenting the work of Sensius. So we are nearly to the end, and I would like to invite Maarten to experience the lighting and the audience in front of him for the last time before the real world work starts at 4 o'clock. So Maarten, please come forward.
Yeah, I guess I have to be standing here. But anyway, it's nice to get the applause then already. So, I'm really pleased by the day. I think we had a great get-together on what we call the research triangle: industry, clinics, and academia. Not said that clinics is not academic, but we do think, and I hope you are convinced as well now, that this is really important. I would sincerely like to thank the speakers, moderator, but also the poster presenters. I think they also presented very great work, and if you haven't seen it yet, then please go when there is the hour break. But I also would like to thank the organization, of course. I will do that later, a bit more. But let's say already on this stage, I would like to thank Danielle and Noortje. I really think that they did a marvelous job. And yeah, I think it's also always important to have the glue in a meeting like this. And I think both of you were that. But it's also great to host so many people here. I think this was our very first, what is it? MedTech Day? But I can already announce that we also will have a second one. So I would also like to invite you all to that second one. I am sorry, my oration will not be part of that one, because I can only do that once. But if there's anybody in the audience still needing to do an oration, then please step forward. We can always integrate it in the program. What else? I guess, yeah, the next point of the agenda is my oration, for which I will heartily like to invite all of you. For now, there will be a bit more than an hour of sort of break. And yeah, as I said, I think it's a nice moment to enjoy coffee, to have more discussion, and specifically to look at the posters. For now, I want to thank you for your presence and already thank you in advance for the next one. Huh? Thank you.
Dan weet ik, moet ik even kijken. Maar
Ja, Maarten Paulides. Ja. Heel goed zelfs. Wij hebben een soort crashcursus samen gedaan. Toch? Herken elkaar. Ja. We hebben samen midden in de nacht afgelopen. Ja. Dankjewel dat je bent. Ja, dat is voor mij natuurlijk wel. Ja. Wel fijn uit. Then maybe how to explain.
Ja, please be seated. Gaat u zitten. Welkom, dames en heren, ladies and gentlemen, welcome. Welcome to all family members, friends, colleagues, students, people who know Maarten, or people who are interested in the topic. Welcome. Welcome to this, what we call the Blauwe Zaal at Eindhoven University of Technology. I'm, by the way, Bart Smolders. I'm the Dean of the Department of Electrical Engineering. And it's an honor for me to give a short introduction into this very interesting inaugural speech of Maarten Paulides. I'd like to start with a word which is very important in the story of Maarten, and that's in Dutch it's called warmte. Warmte. And you can translate it into two ways. The first translation is heat, you know, warmte as we call it, heat. And today we had a symposium about a lot of things, and of course some of the stories also touched upon hypothermia. And I'm sure that also the family members have heard about what it is already from Maarten. But hypothermia is the treatment of cancer using heat with a special kind of radiation using microwaves. And I had a discussion this afternoon with one of the PhD students working on one of the projects of Maarten. And I said to him, I asked him, is this really microwaves? It said operating at 400 megahertz. So I thought it was not really microwaves, but Maarten is going to tell more about them. I would like to tell you how very important this research, his research into hypothermia is. Maarten focuses in particular on head and neck cancer. It's a very complex form of cancer. And worldwide, at least in 2020, this terrible disease was diagnosed in 562,000 people, which is a large number worldwide. Now, with traditional treatment methods, only 4 out of 10 patients apparently are still alive after 5 years. And by means of hypothermia, the cure rate increases by 50% or even more. And that has been shown in practice already. There are also no additional side effects such as tooth loss or any other side effects that you often see with other therapies like radiation or chemotherapy. An increase of 50% or more. Can you imagine how many lives you could save with that? Now, Maarten has been working on saving lives during his whole career. He obtained his master's degree here in Eindhoven. And after that, we briefly kind of lost him to Erasmus University in Rotterdam. After which he returned to his alma mater in 2018, so about 4 years ago. Maarten is, among other positions, currently director of the Center for Care and Cure Technologies, Eindhoven. And of course, he's also chairing one of the professor positions. And we're very proud that he became a professor. During all his research years, he has made great strides in increasing the chance of survival and the quality of life. So, for example, through his work on we also saw it in the symposium, the Hypercolor 3D, which helps neck and head cancer patients worldwide. Maarten finds his motivation in the patients he may be able to help to become healthy again. And we found an interview, given by Maarten, where he was asked what his fight is. And this was his answer. In our clinic, that's what Maarten said, I see the consequences of cancer up close, but also the enormous drive our patients have, even though we are sometimes their last hope. Seeing that in this situation, patients heal or experience relief always gives new energy to make everything even better.
So that's a really personal drive Maarten has. Which brings me back to the second translation of the Dutch word warmte, warmth. And it's this kind of warmte that one cannot express in grants, publications or titles, because it's the warmth that characterizes Maarten in his personal way of acting. He researches with his heart and wants to make the world a little bit better place with his work. Dear Maarten, as a researcher, you're always looking for collaborations, as shown by the MedTech day that you organized today together with some of your colleagues. You see cooperation within and outside your own discipline, and that's the right way, and maybe even the only way forward. You are very driven as a researcher, but above all, you're also driven by love for the people around you. Always keep working with your heart and encourage the people you work with to do the same. And I wish you all the best and a lot of success with the wonderful position that you have obtained, and looking forward to work with you further and to listen to your inaugural speech.
Today I find myself at the very same place where I was in 1997, when I was visiting the open day of Eindhoven University of Technology. And I can still remember walking down the infamous limbo path, having lectures here in this very building, being excited, but also a little scared for mathematics and other things. Thank you, Rector Magnificus, dear Bart, thank you. Thank you, colleagues. Thank you, friends, family. Thank you, all those present here, physically and online. I am honored to be standing in front of you. I had never expected to be this way, but I'm happy to have achieved it. But now, we want to continue. Long ago, when you had a headache, people would put a stingray, an animal like this, up to your scalp to relieve from the pain. They had no idea what they were doing. And in this speech, I would like to argue that with technology, we can now do it in a reproducible, predictable way. I also would like to argue why, and I think it's a bit controversial in this university, I think we should trust more on modeling than on experimentation. Besides that, as a subtitle, I have research in the Golden Triangle. Well, we have heard it before, and especially those visiting the TUE MedTech Day. Because I believe that the only way forward in the medical field, medical technology field, is by collaboration. This research is an honor for me to do. Because, as Bart already mentioned, it's very close to my heart. I really want to use my inspiration for the good of society. If we look at life expectancy, fortunately, it has grown, increased a lot over the years. And the reasons for this is because of improvements in hygiene, nutrition, diet, and also access to healthcare. And technology has an important role in many of those elements. And if we look to the Netherlands, we see that an even further higher life expectancy at this moment is obtained. But we also see a gap. We see a gap between the life expectancy worldwide and the one of the Netherlands. And even in the Netherlands, we also see differences. I believe that technology can make a difference here. I believe that the results we obtain in a few can be translated to many. The other problem we are facing is the constant rising of cost of healthcare. And here again, I believe that medical technology is not the problem, but the solution. Medical technology helps to get similar or better results at lower cost. And especially in my view, electromagnetic waves have a very potent potential. Because electromagnetic waves are very versatile. Depending on the frequency, so the speed at which they operate, they have very distinct properties. Furthermore, they are usually cost-effective. And they are non-invasive, which makes them very nice in non-invasive strategies. So examples of this are, for example, neuromonitoring. MRI, some of you may have had the scan of the knee. But also interventions like ablation therapy with radio frequency or laser, which are all electromagnetic waves used to cure or to monitor or to image patients. And besides, I believe that electromagnetics also has a role to play in bringing everything we know from the hospital closer to the home. For example, in an ambulance, here you see an example of a device which can be used to determine very quickly if a stroke is a clot, so an obstruction, or a bleeding, which is very important for the intervention. This can be used inside the ambulance and is based on electromagnetic waves. So, our understanding of all this, many people think that research works linearly. So you have slow advances and it all goes gradually. If I look in history, it's not like that. It works in waves because we need inspiration. We need each other to progress, and often an idea from one helps ideas from the second and to continue upon that. So in this part, I would like to explain the waves of progress that we have made in history. So first, if I look to bioelectricity, then the first person, well, not the first, or one of the first exploring that is the very well-known Galvani. And he was experimenting with legs of frogs and connecting that to different materials. And then he saw that they started to move, which was very interesting, obviously. And then he thought, well, maybe this energy is inside of this muscle. It's coming out, basically. But then there was Volta, who had a very different idea. No, he said, it's not within, it comes from the outside. It's those two metals which you are connecting it to. And yeah, research has shown that Volta is right. But what fascinates me here is the debate they had and how they got to solutions. And furthermore, I think this is a very nice example of research in biology leading to applications in technology. Whereas we tend to think it's the other way around. It's technology first, then applications in biology. So here you see the battery which he developed, which was based on the experiments in animals. One other thing which I want to mention here is that Galvani in fact wanted to do theology. And yeah, I see myself as a minister a little bit now, so I guess that also connects. But also he was a physician going into physician going into becoming a physician. So he was first in medicine, then going into physics, having really an interdisciplinary approach. And this brings us to, I think, the most important person in biomedical electromagnetics, which is the field we are discussing here, and that's von Helmont. He was truly interdisciplinary. Again, his parents had a big say in what he was doing, because, in fact, he was more or less forced to become a physician. I think at the time people thought that that was the right move, because apparently many were pushed in that position. But he started experimenting, and he was like a self-taught physicist. But as a researcher, he made major improvements. He found a propagation through muscles. He had major improvements, major contributions to the mathematics of the eye. And for me, very important, he found that electromagnetics can induce temperature, can heat, which is one of the two ways. But I think for me what's nice is that he was also an inventor. He developed the ophthalmoscope. Well, this is maybe a difficult term, but everybody going to the optician knows it because it's the device how your eyes are checked. So it's a huge development, a huge invention still affecting modern world today. And he also developed the resonator. Well, the resonator is to find tone, to measure tone. And besides that, for me, is inspirational because he was a great educator. Many of his students, they developed into world-leading scientists. For example, Wien. Wien invented or found that all bodies radiate electromagnetic waves. And this is the basis where still infrared cameras are based on. And Hertz, well, I think Hertz is known. But I think in this story I wanted to say this. I was referring to a physician position. They thought it was very important. Well, physics at that time was maybe less so because EM theory is completely useless. The only thing is that Maestro Maxwell is right, and I'll come to him later. So at the time, I think things are changing. The ideas we have about this are moving. So I mentioned him. Maxwell cannot be left out, I think, here. He developed the classical electromagnetics theory. I'm sorry, Gerard, I have to give you cake because there's formulas there, but which is what we have in our clinic. But those are the famous formulas which we still use every day. He found that light is a wave, which was later validated. But he also had a strong societal drive, which, well, as you may understand now, is also a strong motivation for myself. And what most people don't know, he was the inventor, the first person who made a color image. So he was using this, and I think that's also a nice way of, let's say, having a nice application. So all these people, they knew what was happening, they started to understand it. We started to understand electromagnetic waves, and this was growing in parallel. But we knew how electromagnetic waves behaved outside of the body, or to the outside. And I think for my work, Ken Yi is quite important because he developed the so-called finite difference time domain technique, which is something I've been using a lot in my research. And basically this technique, I won't, let's say, explain everything, but it's built on making very small cubes and sort of approximating in that way by a very clever staggering grid and separating the two components of an electromagnetic field. And using this technology, we could also start understanding what was happening inside of the body. So here I also want to mention Alan Tavlov, not because he developed the method, but he popularized it. So he used it for low frequencies, middle frequencies, and up to light. So he really, let's say, used it in many, many applications. Then, if you can simulate what's happening, of course, you also need to know which kind of values do you need to use for tissues. You have the equations, what to put in them, basically. Well, if you look at electromagnetics at an atomic scale, all tiny scale, it's very, very, very complex. This is about how electron clouds respond to fields. And then there's neighbors affecting also the fields at the one. And so it's really complex. And let's say the fields are also wildly varying. So using that knowledge for modeling is not really at this moment an option. Maybe it comes in future. But at this moment we do it more on a tissue scale. And we are using inference. And I think it's a question of definition, but for me a measurement is a property which you directly can relate. And inference is more like the modeling is a bigger part of the properties which you get. But I think measurement and inference are quite related. But the most important thing to remember is that inference is built on complex modeling to get to understand what's happening and know the parameters which you need to use. So, but still at this scale, we are using effective properties and probe-based measurements, of which the family, Gabriel, those are husband and wife, did a lot of measurements which we are still using today. And again, it's still complex because there's many confounders, and one of those is temperature. So if temperature rises, electrical properties also change, which obviously is important for my work on heating. So this was, let's say, now we have established the models, the knowledge, the models, the properties which we can use. And then this was the first approach where they, in 1980, used this kind of modeling to understand the safety to electromagnetic waves. So if a wave falls into you, what happens, basically? And we also did some work, and Julian Bakker in the audience, he did this. And we were studying what an 1.8 gigahertz wave, which can be used in mobile phone radiation, what it does when it, let's say, comes into a human. And this is the electrical component of the field, which you see, where white is high and black or blue is low. And then you can see that the waves indeed propagate into tissue. And you see that it even reaches the brain. But luckily, this is in a certain scale. And I can assure you, these values are really low. I'm just saying this to show that it can be simulated, not that it's harmful. So if I look back to the waves which we had, then you see we have first we had the understanding in bioelectrics, bioelectromagnetics, then it advanced with electromagnetic theory. We started to learn how to model electromagnetics in tissue. And then the next wave was model-based design, if you relate it to medical technology. And this is the wave where also my waves come into play. So, I'm getting back to this where it started. Where did I get inspired? Well, I guess it was here. And this is the factory of my father. And this is also my brother who took over. So this is where I found that using electricity you can start movement, which was magical. And it was so magical that after finishing my HAVO degree, so my high school, I didn't want to go on a holiday, but I wanted to explore that further. And I did that when I went to Wales, to the Gower. And it's magical because of the waves. Well, I think that fits the theme. But it's also magical because there I was working on drives. So basically those drives, they drive the motors here. So this is like a two-unity, these components. But mainly there I let's say, got in touch with Howard Kinsey, which was the person I was staying at the time. He was also the director of the company. And he inspired me to learn not only more about electromagnetics, but also to go to academia. He really said, what are you doing? Where you're doing? You should go to university. This is where you. And we even made plans to go to the UK I know, somewhere near London, I think, Cambridge, I don't know, but we had concrete plans then. So basically, I didn't do that. I came at this very place, Eindhoven University of Technology. And during my studies, I got more inspired in electrical engineering, but specifically electromagnetics attracted me. And I don't know if it was because it was often seen as the most complex subject, I don't know. I know it was at the time, and I think it still is. But I know also that at the time when I needed to do an internship, this was in the Flux building, I was taking up the elevator because I was going towards the room of Professor Anton Thijhuis. And this was like this dark corridor at the time. The 13th floor, really the highest at the building, coming into the room. And, well, there were stacks of books everywhere and no clean desk principles. It was like stacked with papers everywhere. And we had this discussion or this talk about what can I do on an internship. And I'm very pleased you're here, Anton. But basically what I said is, yeah, I want to do something in electromagnetics and I want to do something useful. And then I saw this face that turned a little red and saying, everything we do is useful. I think you still remember. Okay, but still he was willing enough to help me. And I went to this place where I learned about, let's say, this was a Supélec, which is near Paris. And it's what they call a grande école. And there they were studying using electromagnetic waves to image tissue or things, let's say. And I think the device doesn't look that advanced. But it was nice as an intern. I could really work on it. I was in that water pool doing measurements and soldering, and well, soldering outside. And also I want to mention Jean-Michel Geoffrin, because he really inspired me to go into the biomedical electromagnetics. This assignment was very important to me, and I think it is. I think we as a staff should realize how important these kind of things are when we, let's say, help students go somewhere. This can be really decisive. So, what I also want to mention is, of course, this device was intended to be used as a monitoring device for a hypothermia applicator, which at the time was in Utrecht. That was the intention. So he also taught me about hypothermia, the existence. And I thought, well, that's interesting. I want to know about that. So then I started to learn about hypothermia, that it has a lot of effects, a lot of biological effects. And I can go through all of those, but let's not do that. Let's just say that it's a temperature-dependent effect, multitude of effects. So all these effects are dependent on temperature, and they are very different effects. So they can be stimulating immune therapy, they can stimulate chemotherapy, they can stimulate radiotherapy, or all, depending on which effect you look at. And Professor Zwanborn, unfortunately, is not here. But then I met Gerard van Roon, and we started working on a master project developing the head and neck applicator. Well, Bart told you about it already a bit. These were one of the first simulations we did, where we showed that indeed we can focus energy using, this was 4 sources, I think, at 433 megahertz. Doesn't matter, it's doable. And then based on that, we got the KWF project. So we can start also doing a PhD. And I think what is nice about this consortium is that it combines sort of also academia with the clinicians. So that's the theme of today, the golden triangle. I think it's also in here. So the result of that work was the hypercolor. And let's say we also showed in simulations that with this device we can nicely focus the heat to the target region, where the target is the green contour. So that was a model-based development. So I think what is important here is that for the first time we used the modeling to design the device. So basically we went to the clinician, asked him, Peter Levendag, what he wanted, what he needed, and then designed using modeling the device which fits that. And we also developed, based on that, the model-guided treatment. So in this treatment, what you do is you take a lot of images, CT, MRI, as we said, you know where the tissues are. With that, you can make a 3D patient model. You can do the electromagnetic simulations using, for example, the FDTD technique, which we had before. And we can do optimization, optimizing the heat delivery to the target region. But this is, again, model-guided. And also, we use the modeling to develop prototype 2. And of course, it doesn't look like it was designed, but that's coming. And also, of course, it's important to do the validation. So we validated using electrical field measurements the simulations. And we found in patients that we can increase the SAR, which is the energy delivered to the target, by 50% using this new device versus the old hypercolor device. So that, I think, is a very nice achievement. But you have to understand that this is based on inference. So this is based on what our modeling says we are achieving based on the applied signal settings. So we are using, basically, to determine this improvement, models and measurements. But also in the clinic, we see that, let's say, in the patients we treat, we don't see a difference with if you combine radiotherapy and hypothermia with chemoradiation. It's comparable results for now. Of course, this has to be validated in a larger patient group, but that's what we see. We see similar or better. And importantly here is, of course, if you look at chemotherapy, it has a lot of side effects. Whereas the hypothermia doesn't have that. If you apply it well, it doesn't have side effects. So this work was the basis for Sensus. Those of you who are here the whole day, you have seen it already. And to design this device. And why do I think that this collaboration is so important? Well, it's because of the way we do evidence. If you want to get up in the scale of evidence, level 5 is the lowest, level 1 is the highest, you need to do so-called randomized controlled trials, where you expose some patients to the treatment and some you don't. And basically you compare those two groups, and it's randomized. You do by chance you determine which one is treated and which one is not, so you have comparable groups. But to really demonstrate this, you need big groups of patients. And the only way to do that is if you have multiple clinics working together. Well, those clinics need a device. And this device can only be delivered to multiple clinics if you have a company. So here the company is really a necessity. So here, if you look through the path towards widespread adoption, you see that we made a number of strides. And I'm happy to say that based on the retreatment, so hypothermia given to the second time radiation, first time failed, second time radiation with hypothermia, we are now also, let's say, developing a study where we really apply the temperature, the heating, to first time radiation, which is a major step. And I've been talking about hypothermia all the time, but there's many other ways, let's say applications, where you can apply the same procedure. And this is neuroscience, which is, let's say, a topic I got into when I started here in Eindhoven. And I have two examples where I think the model-guided design really pays off. And the first one is, together with Rob and Massimo, we are looking if we can use a new type of focusing using the nonlinearity in biology. So really understanding biology, what it does, and using that nonlinear nature to focus the neurostimulation. And why is this so important? If you normally do neurostimulation now from the outside, then you use long waves, so you also focus it at a very big region. And what we want to do is stimulate a very small region. And here we are exploiting the nonlinearity in biology to be able to do that on a precise way. Well, that's the hope. The second application where we are looking at this moment is to restore vision. And we are in a big consortium looking if we can, let's say, people who are blind can restore that again by placing a camera and then injecting those signals directly at the visual cortex. So not going from the eye through the visual, towards the center of the brain and then outside to the visual cortex and then interpreting, but to go around that by technology. And here, again, this is work with Sander and Leroy. And again, this is an example where the modeling plays a crucial role. Now, I discussed in the neuroscience application a little bit about using nonlinearities in biology. I think that will be a recurring theme. I think from now we will shift from EM, model-based design, towards bioelectromagnetic model-based design. So basically understanding and being able to model what's happening in biology. And I think the first application here is already what we have been doing in hypothermia. So we have been trying to understand what temperature is doing, which the temperature is, and we do that by placing probes. Well, probes is obviously uncomfortable for patient. You cannot pierce a lot, and you have information only at the probes, so only few locations. And we try to solve that by modeling, but what we can model is the electromagnetics part, not the thermal part. And what is more important, if you look at hypothermia, the most effective part is between 42 and 43, depending on which treatment you combine it with. If you combine it with chemo or radiation, the optimum temperature can be different. For example, in immune therapy, you need a lower temperature. Radiotherapy, it's higher. But in essence, it should be a well-defined temperature. And we cannot do that by the technology at this moment. So therefore, we refer to MRI, magnetic resonance imaging. And on the right-hand side, you see the image. And indeed, Ruben, this is the picture of you. And well, I was not allowed to say that he can explain everything about MRI. But what for me is important is that we can measure anatomy with it, know where the structures are. But moreover, we can also measure temperature with it. And here you see an example of, let's say, a tumor in the leg. And you see a red contour indicating where the tumor is. And you see in the color scale, so the red is, let's say, where there's heating, and then gradually going to the blue where it's not heated. So you can see that we can nicely track that. This technology is very powerful. So we wanted to also develop that for the head and neck, because in the head and neck we want to focus very tightly, so we need to know exactly what's happening. So that's why we developed the MR color. And there is a poster outside, so if you want many more details, you can look. What we also developed is integration of MRI coils inside the device. Well, this sounds like an easy job. It's not, because we had to redevelop the whole antennas and then integrate those dedicated coils into it. And luckily enough, it works. And before explaining this, I should say that the temperature measurement is a very subtle measurement. There's a lot of confounders which can affect this temperature measurement. So it's very important to have a very high signal to the noise. You want a very strong signal, and you don't want the result to be affected by noise. And what we showed is that indeed, if you look at if you use the traditional setup on the left, then you see a very grainy image in the region of interest, which is, let's say, the phantom where the patient should be. And on the right-hand side, you see that it's much clearer. And also the SNR image shows that there is a 5-fold increase. Well, this directly translates in 5-fold increase in imaging speed. And why is that important? Well, if you do a head and neck treatment, the patient doesn't fully lie still. It has to breathe, it has to swallow. And to be able to correct for all that, you need the image really fast. So the faster you can go, the better you can correct for those kind of, let's say, influences. So here, this 5-fold increase directly translates in faster imaging and therefore less artifacts. And let's say the importance of those kind of things I can show here, where we see the temperature profiles during pelvic hypothermia. And then you see that at baseline there is very little temperature. After 50 minutes, you see that indeed there is let's say, a heating zone. But you also see that there's a lot of, let's say, artifacts. And especially at the front, for example, there is gas moving, and there is intestines, and there's all kinds of motion. These affect the imaging. And in some patients, it's even worse. You really have signal, what we call the signal void. The signal is fully out. You don't see anything. So this is a big problem for us. And how do we want to solve that? Using the modeling. So here you see some images on the left with the MR thermometry, the magnetic resonance temperature image. And there's the unfiltered, the filtered, which was, let's say, the filtered one is the approach we already developed as an improvement for the clinical. And then on the right, you see the POD Kalman approach. Well, you can forget about that. What you can remember is that it's really using the modeling, knowledge from the models, combined with the measurements, and together you try to estimate what the best temperature distribution is. And with that, we can really see that it's much smoother pattern. But we can also see that there are some regions where there's no, where the POD Kalman results were a bit, inaccurate. So at the arrows, those are the places where the model was incorrect, basically. So we need to improve the model at those locations. And we know how to do that, but this is, let's say, work in progress. So here, this is a very nice collaboration we have with the lab of Maurice Hemels, where we are looking if we can use those images also in a direct feedback loop. So we are studying if model-based predictive control can be used to guide the heating settings based on the measured MR thermometry distributions. As we said, the problem here is that we have the artifacts and the motion, the missing data and the motion artifacts, so these we have to account for. So that's where the POD Kalman came in, to improve that, to get a better estimate. And let's say the improvements in the model, for example, where the patient lies, is something we can also improve. Because the MRI is not only a temperature measurement device, you can also measure anatomy. Where is the patient inside the device? So based on that, we can also correct the model in real time to have a better estimate of the electromagnetic distribution and hopefully then also the thermal distribution. So what we are looking at is ways to do this directly during treatment, so to accelerate all these simulations, which can take hours and hours, into seconds or minutes. And the idea is then to, based on the anatomy of the patient inside the device, to resimulate and to use that as an addition to the measurements. So really have a combined effect. And yeah, for example, here we are using artificial intelligence principles, also physics-based. And at this moment, it's unclear where, let's say, the optimum is. But we are investigating multiple approaches. So if I look here, then the MRI to me is a very powerful machine in bioelectromagnetics, because it helps to infer the bioelectromagnetic tissue properties during treatment. So using this modeling and this feedback control, we also start to understand what the tissue is doing during treatment and start to get those data. And this data we can use later on to model when we don't have the MRI. So for me, it's not only a guiding machine, it's also a learning machine. Yeah, and I believe that it's not only bioelectromagnetics where we can use this, but also biophysics broader. For example, if you look in the mechanical domain, you can apply this also to focused ultrasound applications, but there are many more here. I think we should work on very good inference techniques, very good MRI techniques, to be able to get all this data out and to understand and quantify really what's happening. Now, why do I think that's so important, the modeling? Because if you look at how devices today are being developed, it's often a very iterative process. You saw it also in my, let's say, the work I did. We developed something, then, let's say, applied it, and then still had to adjust, basically. And you want to get all those adjustments out. Because, yeah, it's time-consuming and costly to do all these iterations, especially if you see that for all these devices you have to do studies to understand if they are safe, if they are effective in animals and patients. And basically you don't want to do that, or you want to minimize it. And this is even more pressing because since 2021, there's the new MDR in place, which makes that every new device we are using in the clinic also has to do a sort of a pre-CE. And the CE is the certification which you need to have before you can sell it on the market. And basically this pre-CE is almost equivalent to the CE. And before it was not. So before it was much less time-consuming, costly, and now it is. So I think, let's say, we should get this blockage out because it's a potential hurdle for European medical technology industry by using the modeling. Yeah? By really inferring those values and design the device right at the first time. In this way, I think that the biophysics can be, let's say, a way around the roadblock of all these iterations. So therefore, I believe that we should start collaborating, a theme of today, with many clinics, industry, academia, to be able to get standardized measurements during therapy, to understand what's happening, to know what's happening, to do large-scale data collection, preferably in open source databases, if we can. Then start working on advanced processing and inference techniques to get all the relevant quantities out. and make, let's say, open source available tissue models and databases, and in that way help new device designs. In my view, this is the only way in hardware medical technology to overcome the new hurdles. And besides that, I also think we should start training our designers in a different way. I think in Eindhoven we are already doing it, but I'm infected, I guess, already. So I really want to advocate that we need specialties to start intertwining. And in large enterprises, you see that already now there's multidisciplinary teams. There's individuals with expertise from different sides, electronics, mechanics, but also clinical. They are brought together, or design, industrial design. They are brought together to make the new device. But for, let's say, large companies, that's doable. You can bring all these expertises together. But for small and medium enterprises, and exactly those are the ones developing all the newest technologies with the more risky approaches, so important for improving, I think we should start developing interdisciplinary or teaching interdisciplinary designers. And those are, in my view, M-shaped. So they understand the whole pathway from ideation, design and verification, clinical evaluation to commercialization. So this whole pathway. But they also have a detailed understanding of bundle-based design. And here I think that the triangle, of course, is very important. Because, yeah, for the large enterprises, you are doing that collaboration, but training those individuals interdisciplinary, you can only do in the Golden Triangle, with industry, with clinics, and here. So I believe that we are looking at the new wave on biophysics model-based design, which enables designing effective and cost-effective medical devices. I believe that standard MRI-guided treatments enable to infer the bioelectromagnetic and biophysics tissue models under treatment conditions. And I also believe that if we want to exploit this new wave, we should start training the interdisciplinary designers, and the collaboration is really important. And I also think that we should do this not only for the Netherlands. It's really important that technology takes its role, not only to improve our situation here, but also in the whole world. And that's why I want to conclude this part with we must constantly realize that time is always right to do what is right. Now, you were hoping I was finished. I have a few things I still have to say. Well, first of all, I want to thank a few people, and I want to do that by starting with this image, because this is when I climbed together with my brother-in-law, Rick. We climbed the Albula, and this is a very nice path, because what you see is there's a winding road between the very nice nature, and it's very nice that after each corner you see a complete different view. And to me that resembles my scientific career, because every corner brought new insights. And at every corner there were also new people to inspire. And those people I would like to thank here. So first of all, I have to start with Gerard. Because you were my mentor. You taught me everything there is to know about research, especially also clinical research. But in general, I want to thank Erasmus Medical Center, Remy Naut, and all the others who taught me that the clinician's point of view, a patient's point of view, is really important in developing new medical technology. But I want to thank you. I'm very lucky that I got here, because now I get the opportunity to, let's say, go along in this flow of collaboration, which I really like. And I also admire the way you still stay calm, whereas you have so many duties. I also want to thank Massimo Misci and Jan Bergmans for teaching me how to do research in the Golden Triangle. And with Jan, I also want to mention Bert, who is sort of together. Jolie for taking out all the things we don't want to do. Carmen, I don't know where you are, but ensured for the MedTech collaboration, which I think is really important for us. Of course, the research lab, and here specifically I want to mention Rob Mestrom, because he, in my view, is the core of the lab. And also Deborah Rivera for her inspiration, also for this talk. The collaboration with Ghent, I think, is really important to us. But also international, I couldn't mention everybody, sorry about that, but of course Sensius, the companies, the medical centers who I'm working with. I've been so lucky to have so many mentors and people guiding me along the way. Of course, I have to thank the true giants of the research, because they did it. These are all the PhD students and the people I was fortunate enough to supervise. I want to thank the center, specifically Noortje and Danielle. I already did it, but they are very important for the collaborative atmosphere we have in this department. I also want to thank my family, my extended family, or I would say also family, my friends, for all their support. And of course, I want to thank the ones who inspire me every day, which is Petra, my wife. She keeps me with my head in the clouds, my feet on the ground. And also Ruben, the leader, Elise, the creative, Noelle, the moderator. I will explain, ik zal het allemaal uitleggen, meisje. I also want to thank the patients, because without patients we cannot do any research. And this is one which we got from a patient, a plaquette, which inspires, I think. And I would like to end with one of our heroes, James Clerk Maxwell, saying, "The only desire which I can have is, like David, to serve my own generation by the will of God." Thank you.